Well, you actually know, it's actually a little bit confusing at that point. They could be, in fact, very widely separated in both space and time, but in such a way that a light beam could connect them. Okay, so there's a lot of information encoded in that. Now, as we move forward, hang on a second. As we move forward, we're going to upgrade this. Okay, so right now our metric is just this simple matrix of -1s, 0s, and 1s. One of the things that we're going to do is sort of a warm-up exercise. The more complicated things we're going to do later is we're going to move away from special relativity and Cartesian coordinates. We're going to look at it in polar coordinates. That's going to be kind of like a warm-up zone. And so when we do that, we're always going to reserve eta for the metric of special relativity when I'm working in Cartesian coordinates. Okay, it's a great symbol to have for that, and it's a useful thing to always have that definition in mind. I can continue to do special relativity, but then working in coordinates that are spherical-like or polar-like or something like that. Then this is going to become a function. Okay, and what that is going to mean is that things like my little basis vectors are going to have more complicated behavior. A little later in the course, we will then show that when gravity enters into the picture, essentially the essence of gravity is going to be encoded in this thing as well, in a way where, again, it's going to be a function. It's going to vary as a function of space and time, and the dynamics of gravity will be buried in that. Sort of funny that it really does just sort of start out. I mean, if you take that thing and you set delta t equals 0, this is just the bloody Pythagorean theorem. Okay, that is all this is. Put time back in, and it sort of is the generalization of Pythagoras to space-time. And in fact, we're going to take advantage of that and sort of define a geometry that looks like this as being flat in the same way that a board is flat, and the Pythagorean theorem works perfectly on it. Then we're going to start thinking about what happens when it becomes curved. And you start thinking about things like, what does the geometry on the surface of a sphere look like? Okay, that's just sort of pointing ahead. So I just throw that at you so that you get ready for some of the concepts that we'll be talking about soon. So let me write this actually in terms of differentials. It's sort of useful for what I want to say next. So a little differential if I have two events in space-time that are very close to one another. I can write them like so. And what I've essentially done here is written dx as dx alpha E alpha. Before I get into some more, sort of a couple of important, physically important 4 vectors, the reason I did this is I want to make an important point about some notation and terminology that is used. If it is the case that the displacement vector is related to the differentials of your coordinates like so, we say that E alpha is a coordinate basis vector. What it does is it transforms a differential of your coordinate into a differential of a differential vector in space-time. Now you might be thinking to yourself, okay, well, what other kind can there be? Well, this is where my little spiel there a second ago about how we're going to start looking at more complicated things is going to become important. So when we're working in a Cartesian-like coordinate system, the fact that this is what we call a coordinate basis vector isn't very interesting. Suppose I was working in some kind of a curvilinear coordinate system, okay, spherical coordinates. And let's just focus on 3 space for a second. So if I write out a sort of analogous equation in curvilinear coordinates, okay, so here's the three-space version of that. And let's imagine that I equals 1 corresponds to radius, I equals 2 is theta, I equals 3 is phi. Then this would be dr er plus d theta e theta plus d phi e phi. Does that disturb you at all? Okay. This has the dimensions of length. These have the dimensions of angle. In order for this to work, ER must be dimensionless, E theta must have the dimensions of length, E phi must have the dimensions of length. This is the form of a base. This is what a coordinate basis looks like when I am dealing with, well, we're going to use this a lot in this thing. So this is, I introduce this right now because you are all probably looking at that, and some small part of you inside is weeping, because what you want me to write down is this. Isn't that better? Okay? This looks like something you're used to. So I throw this out here right now just because I want to make sure you're aware that there are some equations and some foundational stuff you guys have been doing over the years. Particularly, this shows up a lot when you've done E&M out of a textbook like Purcell or Griffiths or Jackson, because there's some derivative operators which are assuming that your basis vectors are what we call orthonormal. So my EI hat here, it is an orthonormal basis. An orthonormal basis is defined such that the dot product of any two members of this thing gives me back the Kronecker delta. Okay? That is not necessarily the case when I work with a coordinate basis. Our basis has ER dot ER equals 1. Yay, that one's nice. But when I do E theta dot E theta, I get R squared. E phi dot E phi will be R squared sine squared theta. And what I'm going to do when I start generalizing these things, I'm going to change my, this thing which I defined up here. See, I still have it on the board. Yeah, right here. So when I said eta alpha beta is E alpha dot E beta, and I made it this thing, I'm going to generalize this and say that the dot product of any two basis vectors, it gives me a more general notion of a metric tensor. And the values in the metric tensor may be functions like this. Okay? Right now, throw that out there. This might be sort of like just like a peek of the horrors that lie ahead. Okay? We're not going to worry about this too much just yet, but I want you to be prepared for this. In particular, it's really useful to have this notion of a coordinate basis versus an orthonormal basis in your head. Okay? We're going to start defining some derivative operations soon. In fact, probably won't get to them today, but they will be present when we start doing lecture 3. And there's a couple results that come up where everyone's sort of like, wait, I knew that the divergence had a factor of r on that derivative there. Where'd it go? Okay, it's because we're not working in an orthonormal basis. All right. I'm a little sick of math, so let's do a little physics. So far, the actual only physical 4 vector that I've introduced is the displacement vector. from the displacement vector, it's really easy to make probably the first and simplest important four vector, which is known as the four velocity. This tells me the rate of displacement of an observer as this person moves through space-time per unit, and we're going to be careful about this in this class. D tau is the time interval as measured along the trajectory of the observer with four velocity u. In other words, that's a very long-winded way of saying it, it's an interval of proper time. In English, the word proper time sounds very like, ooh, I don't want to use improper time, I better use that. But this actually, I think it comes from French, and it just refers to the fact that it's one's own time. Apparently in German, people say Eigenzeit. So, there's a couple of different words for it. But proper time is what we use. In special relativity, if we see someone going by with constant velocity, a particular observer who sees, we're here in the room, someone comes through, their four velocity is u, we would see their four velocity to have the components gamma, gamma v, okay? Where gamma, I'll remind you, is the special relativistic Lorentz factor. And I'll remind you again, we've set speed of light to 1. A very useful thing, which we're actually going to take advantage of quite a bit, is that in the rest frame of u, in the rest frame of u, or I should say of the observer whose four velocity is u, okay, they just have 1 in the time-like direction, c if you want to put your factors back into there, and that's basically saying that the person is standing still but moving through time. Okay? Because you are always moving through time. All right. From the four velocity, for an observer who has, or for an object, I should say, who has some mass, we can easily define the four momentum. Where this m is known as the rest mass of this object. It's worth a bit of description here. You'll often see, particularly in some older textbooks that discuss special relativity, people like to talk about the relativistic mass. Okay, and that comes from the fact that if I write out what this thing looks like according to some particular observer, you have this gamma m entering into both of the components. And so older textbooks often call gamma m the relativistic mass. That's not really the way people have, over the course of the past couple decades, they've moved away from that. And it's just more useful to focus on the rest mass as the only really meaningful mass, because as we'll see in a moment, it's a Lorentz invariant. Okay, we'll see how that is in literally about 3 minutes. And so what we're instead going to say is that as seen by some particular observer, this has a time-like component that is the energy that that observer would measure, and a set of space-like components that are the momentum that that observer will measure. So where we get a bit of important physics out of all this stuff is by coupling these two four vectors to the scalar product that we made up. So the first one, if you do u dot u, according to any observer, that's just going to be minus gamma squared plus gamma squared v squared. And with about 20 seconds worth of analysis, you can find that this is always equal to minus 1. Actually, there's an even trickier way to do this. Suppose I evaluate this in the rest frame of the observer whose forward velocity is u. Well, in the rest frame, v is 0 and gamma is 1, and I get minus 1. And this is an invariant, so whatever I get in that particular frame must be obtained in all frames. That's a trick we're going to use over and over and over again. Sometimes you can identify, you get some kind of god-awful expression that just makes you want to vomit, but then you go, wait a minute, what would this look like in frame blah, blah, blah? And you sort of think about some particular frame, and in that frame, it may simplify. And if it does, and it's a frame invariant quantity, mazel tov, you have just basically won the lottery. You've got this all taken care of. Go on with your life. So the forward velocity has a scalar product of itself that is always minus 1. Okay? How about the forward momentum? Well, the forward momentum is just forward velocity times mass. So that's just minus m squared. But we also know it's related to these two other quantities which are important in physics. This is related to the energy and to the momentum. So this is also equal to minus e squared plus, so this is the ordinary the magnitude of the 3 vector part of this thing as measured by the observer who breaks up the forward momentum in this way. So what this means is I can manipulate this guy around a little bit here. Anybody who works in particle physics is presumably familiar with this equation. Sometimes it appears with the p squared moved onto the other side. Okay, if it looks a little bit unfamiliar to you, let me put some factors of c back in this. So remember, we have set c equal to 1. When you put it back in, that's what this is. So it drops out of this in a very, very simple way. One of the uses of this, and many of you have done exercises, presumably in some previous study that does this, and there'll be one exercise on the PSAT that was just posted where you exploit this. So a key bit of physics, the reason why we care about forward momentum is it's in one mathematical object allows us to combine conservation of energy and conservation of momentum. So conservation of forward momentum puts both conservation of energy and conservation of momentum into one mathematical object. So if I have n particles that interact, then the total forward momentum is conserved in the interaction. Okay? So, yeah, we talk a little bit more about this and then just sort of quickly move on. So we combining this with the fact that we are free to change our reference frames, often it gives us a trick that allows us to really simplify a lot of analyses. So if I have n particles that are sort of swarming around and doing some horrible bit of business that I need to study and I need to have a good understanding of, we can often vastly simplify our algebra by choosing a special and very convenient frame of reference in which to do our analysis. Choose the center of momentum frame. So this is the frame in which that p tote, so COM, center of momentum, has zero spatial momentum. Okay? In that frame, you have just as much momentum going to the left as going to the right, just as much going forward as going backward, just as much going up as going down. And so this tends out to be, so the classic example of where this is really useful is when you're studying particle collisions and you're looking at things like the production of new particles. So imagine you've got particle A with some form momentum PA coming in like this. Particle B's got some form momentum coming in like this. These guys collide, and they do so. I work in the center of momentum frame. I might want to just calculate the energy at which they just happen to produce some new pair of particles at rest. That would like define the threshold for this particular creation process. Okay? So you're going to play with one problem on the P set that's kind of like that. Let's see. What do I have time to do? I think I will do, yeah, I think I can do two more things. So all the dot products that I have been talking about so far have been a dot product of a 4-vector with itself. Okay, I did U dotted into U, I did P dotted into P. I invented a frame in which P has a particularly simple form, and then when you actually do some of the analysis, you would probably take that P tote and dot it into itself. I haven't done anything that looks at, the crossing between these two things, okay, dotting one into the other. So let me go through a very useful result that follows by combining P with U. There are a very specific notion of P and a very specific notion of U. So let's let P be the form momentum of a particle, I'll call it A. Let's let U be the 4 velocity, not of A, but the 4 velocity of observer O. Okay, so particle A might be a muon that was created in the upper atmosphere and is crashing through our room right now. Observer O might be your hyperactive friend who is jogging through the room at half the speed of light. Question I want to ask is, what does O measure as the energy of particle A? So the naive way to do this, which I will emphasize, is not wrong. Okay, what you might do is sort of go, okay, well, we're sitting here, this room is our laboratory. I've measured this thing in my lab, so I know P as I measure it. I can see O jogging by, so I know O's forward velocity as I measure it. So what I should do is figure out the Lorentz transformation that takes me into the rest frame of O. Once I have that Lorentz transformation, I'll apply that Lorentz transformation to the 4 vector P. Boom, that will give me that energy. Okay, that will work. That will absolutely work. But there's an easier way to do it. So one thing you should note is that everybody represents that 4 velocity as an energy, they represent the 4 momentum as an energy and a 3 momentum. In particular, though, they represent it as the energy that they would measure and the 3 momentum that they would measure. So that means P, as seen by O, is E according to O, and P according to O. That E according to O is what we want. And I just told you a moment ago, if you have P in your own reference frame and you have U in your own reference frame, you can do this whole math with Lorentz transformations and get it out. But you also know that in O's own reference frame, O represents their 4 velocity as 1 in the time-like direction, 0 in the spatial direction. So what this means is if I go into O's reference frame, if I go into their inertial reference frame, notice that if I take the dot product of P and U, I get E times 1 and P times 0. So that is just negative. It's exactly what I want, modulo a minus sign. And so you go, okay, well, I'll flip my minus sign around. And you think, okay, great, but that's, I did that using those quantities as written down in O's reference frame. And then you go, holy crap, that's an invariant scalar product. I'm done. Mic drop, leave the room. What this means is you start with P as you measure it, U as you measure it, take the scalar product between the two of them, boom, the answer you want pops out. No nonsense with Lorentz transformations. None of that garbage needs to happen. You just take that inner product and you've got it. Okay, so that just sort of says in words, no matter what representation you choose to write down P and U in, take the dot product between the two of them, throw in a minus sign, you've got the energy of the particle with P as measured by the observer with U. It's sort of late in the hour and a half, I should say. So let me just sort of emphasize. There are occasional moments in this class where if you're dozing off a little bit, I suggest you pop up and tattoo this into a neuron somewhere. This is one of those moments. Okay, this is a result that we're going to use over and over and over again because this holds. This isn't just in special relativity. Okay, we are actually, when we start talking about the behavior of things near black holes. There's going to be a place where I basically at that point say, well, I'm just going to use the fact that the observer measures an energy that is given by, and I'm going to write down that. Okay? The dot product that's involved is a little bit more complicated because my metric is hairier, but it's the exact same physical concept. Okay? Let me just do one more, and then I'm going to talk without getting into the math about what I will start with on Tuesday. Last for velocity, which is probably useful for us to quickly talk about, is, so we've been doing, we've talked a lot about for velocity. That is just one piece. When we're talking about sort of the kinematics of bodies moving in space-time, you need more information than just velocity. Sometimes things are moving around. There's additional forces acting on them. And so we also care about the for acceleration. And so this is what I get when I take the derivative with respect to proper time of the for velocity. Okay, so there'll be some homework exercises that use this. The main thing which I want to emphasize to sort of conclude our calculations for today is that when I talk about a for velocity of acceleration, this has an extremely important property. It is always the case that A dotted into U equals 0. If you're used to sort of three-dimensional intuition, that may seem weird, okay? Anytime you see a car accelerate from a stop, that's a case in which its acceleration is clearly not orthogonal to its velocity, okay? But the issue here is this is not a spatial dot product. This is a space-time dot product, and some of your intuition has to go out the window because of that. It's very simple to prove this. Remember, u dot u equals -1. So d of u dot u, d tau, which is just 2 u dot a, is the derivative of -1, which is 0. Okay? So this is something that we will exploit if you want to describe the relativistic kinematics of an accelerating body. This is a great thing that we can use to exploit. You often need a little bit more information. Okay? We have to give you as a bit of additional information, some knowledge about what the orientation of the acceleration is and things like that. Okay? So there are, whenever you are given, I'll get to in just a second, whenever you're given any kind of differential quantity like this, it's not enough to know like the acceleration, the velocity. You have to also have boundary conditions, okay? And that sort of tells you like what the initial direction is. Question?
Is the time still the proper time?
That time is the proper time, yes.
So it's like accelerating.
That's right. So you can still define a proper time for an accelerating observer. It will not relate. Hold that thought. You're going to play with this a little bit more on a future problem set. I mean, the key thing is that the way, if you have an accelerated observer, an interval of proper time as compared to an interval of time for someone in a rest frame that sees this person accelerate away, the conversion between the intervals of time the two measure, it evolves. Okay? So, let's say you're in this room with me. In fact, it turns out that if you accelerate at 1g for a year, you get to very close to the speed of light. Okay? So let's say that you were in a rocket ship right now that launched at, with an acceleration of g. Initially, you and I synchronize our watches. And so an interval of a second to me is the same as a second to you. Half a year later, you're moving at something like half the speed of light, and I will see a noticeable time delay. Your interval, an interval of a second as you measure it, looks long compared to me. A year, 6 months later, you're actually quite close to the speed of light, and it gets dilated even more. So last thing which I'm going to say, and I'm not going to get into too much detail with this yet, is we're going to begin next time by making a little bit more formal some of the notions that go around. So we just talked about, we've introduced some physics and some vectors. I've given you guys one tensor so far, the metric tensor. So I'm going to give you, in fact, I will write down a very precise definition of this right now, and we'll pick it up from there on Tuesday. Basic idea, so you guys have seen, the one tensor you've seen so far is the metric tensor. And what the metric is it's sort of a mathematical object that I put in a pair of 4 vectors, and it spits out a quantity that is a Lorentz invariant scalar, okay, that characterizes what we call the inner product of those 2 4 vectors. More generally, I'm going to define a tensor of type 0n as a function or mapping of n 4 vectors into Lorentz invariant scalars. Which is linear in each of its n arguments. So I will pick it up here on Tuesday. Let me just say in words, the metric is a 0, 2 tensor. I put in 2 4 vectors. It spits out a Lorentz invariant scalar. We're going to, before too long, come up with a couple of things that involve 3 real vectors. Excuse me, 3 4 vectors. Too many numbers here. A trio of 4 vectors, which it then maps to a Lorentz invariant scalar. Some of them will take in 4 4 vectors and produce a Lorentz invariant scalar. Notice I wrote this in a sort of funny way. The 0n sort of begs for there to be sort of a n0. Okay? To do that, I have to introduce a dual, an object that is sort of dual to a vector. Okay, we're going to talk about that. Those are objects called one-forms, which actually happen to be a species of vector. We're actually going to then learn that the vector is itself a tensor. And so we will make a very general classification of these things, and we'll see that vectors are just a subset of these tensors. And at last, we'll sort of have all the mathematics in place. We can sort of lose some of these distinctions, and just life goes on, and we can start actually doing some physics with these. All right, I will pick it up there on Tuesday. All right, welcome to Tuesday. So hopefully you've all saw the brief announcement I sent to the class. I have to introduce a colloquium speaker over in astrophysics basically at the second this class officially ends. So I will be wrapping things up a little bit early so that I can take into account the spatial separation and get back there in time to actually do the introduction. I've already posted the lecture notes of material I'm going to be covering today, and probably spill, I hope to wrap it all up today, but it's possible we'll spill a little bit into Thursday. So if you've already looked at those notes, today will essentially just be sort of my guided tour through that material. So I want to pick it up with where I left things last time. So we covered a bunch of material that, again, I kind of emphasize what we're doing right now is just laying the mathematical foundations in a very thorough, almost excessively thorough way, in order that we have a very strong structure as we begin to move into more physically complicated situations in the special relativity that we're focusing on right now. And so we talked about this definition of an inner product between 2 4 vectors, 2 vectors in space-time, okay? And it looks just like the inner product between 2 vectors that you are used to from your Euclidean 3-space intuition. It's just that we have an extra bit there that enters with a minus sign having to do with the time-like components of those 2 4 vectors. And then using the fact that I can write my 4 vector as components contracted onto elements of a set of basis vectors, I can use this to define a tensor, which I will get to the mathematical definition of more precisely in just a moment. The dot product of any 2 basis vectors, I will call that the tensor component eta, alpha, beta. Okay? And so this is the metric tensor of special relativity, at least in rectilinear coordinates. Rectilinear basically just means Cartesian, but throwing time in there as well. Okay, when we start talking about special relativity in curvilinear coordinates, it'll get a little bit more complicated than that, and I will not use the symbol eta in that case. I'm going to reserve eta for this particular this particular form of the metric in this coordinate system. And of course, when you actually write out these components, a very compact way of writing this is just the matrix that has the elements -1, 1, 1, 1 down the diagonal, and zeros everywhere else. Okay, so this is a fairly common way of writing a diagonal matrix. This just takes into account the fact that there's zeros everywhere else. Okay, so I call this the metric tensor, which kind of begs the question, what's a tensor? So this is where we concluded things last time. I'm going to generally define a tensor of type 0n. We're going to change that 0 to something else by the end of today's lecture. You'll be able to see where I'm going probably from a mile away, but let's just leave it like this for now. So a tensor of type 0n is, you can think of it as a function or a mapping of n vectors into Lorentz invariant scalars, which is linear in its n arguments. Okay? So the inner product clearly falls into this category. If I think of A dot B, let's say this inner product is some number lowercase a. A will be a Lorentz invariant. Okay? I forgot to state this, but the reason we defined the inner product in this way was that we are motivated by the invariant interval in space and time between two events. We wanted to find an inner product that duplicates its mathematical structure. If I take one of these vectors, multiply it by some scalar, linearity is going to hold. This will just be eta alpha beta. Okay, this is terrible notation. I'm using the symbol alpha for both a prefactor and an index. -5 points to me. Let's call this gamma. Okay, you can quickly convince yourself that just comes out and you get a factor of gamma on this. You can do the same thing on the second slot. If I take the dot product of A with the sum of two vectors, okay, et cetera. You can keep going. All the rules for linearity are going to hold. I'm not going to step through them all. You can sort of see where they all go. So whenever I'm going to define a tensor, in my head, I'm imagining it's got properties like this that come along for the ride. Now, especially when you see this defined in certain textbooks, MTW is particularly fond of doing this. So we come back to this idea that it's sort of a function or a mapping. You can almost abstractly define the tensor as a mathematical sort of machine that's got two slots in it. So several of the recommended textbooks will write down equations. I'm going to put two lines over the symbol to sort of, if you actually read this in, for instance, MTW or Carroll or something like that, this will be written as a boldface symbol. It's hard to do on the blackboard, so I'm just going to write double bars over it. So if I imagine this with my slots filled with these, it's got two slots associated with it. I fill it with those two vectors. That is equivalent to saying A dot B, which is equivalent to it in this component notation, something like this. So we have repeatedly, in the little bit of time we spent together, I should say I have repeatedly, in the little bit of time we spent together, emphasized the distinction between frame-independent geometric objects, things that reside in the manifold and have kind of an integral physical geometric sensibility of their own, and their representations. I have emphasized quite strongly that you should think of the vectors A and B as being geometric objects. Okay, this is something that is pointing in space-time. We all agree that this points, if that's a displacement vector, it points from event from event 1 to event 2. Okay, everyone agrees on that geometric reality of this. Different observers may represent it using different components. Okay, and that's just because they're using different coordinate systems. So when I write down something like this, so let's go back to the way I wrote before. This is going to turn into some frame-independent Lorentz scalar A. So this is what I like to call a frame-independent object. Frame or Lorentz-independent geometric object, as is this scalar. And so therefore, the tensor must be a frame-independent geometric object as well. Okay? That's a lot of words around the blackboard, but I really want to nail that point home. So tensors, just like vectors, think of them as geometric objects that have an intrinsic sort of geometric meaning associated with them that lives in space-time. We will talk about certain examples of them. Okay, you guys all have some intuition about vectors because you've been doing vectors ever since you took your first kindergarten physics course, and so you know that there's some kind of an object that points in a certain direction. Tensors are a little bit more challenging in many cases to develop an intuition for. Okay? Some of them really do have a fairly simple geometric interpretation. You can kind of think of them as, for instance, we're going to introduce one in a little bit, which describes the flow of energy and momentum in space-time. And so it'll have two indices associated with it, and those indices tell me about what component of energy or momentum is flowing in a particular direction. Really easy to interpret that. Some of the others, not so much. Okay? Nonetheless, they do have this geometric meaning underneath the hood. And that's bound up in the fact that if I put frame-independent geometric objects into all the slots, I get a real number, a Lorentz invariant number out of it. It's the only way that that can sort of work. But one of the reasons why I'm going through this is that just like with vectors, different observers, different frames will get different components in general. So there will be different representations according to different observers. Write down the same thing. Representations. So if you want to get a particular observer's components out of the tensor, there's actually a very simple recipe for this. All you do is you take your tensor, and into its slots, you plug in the basis vectors that that observer uses. Okay? So if I want to get the components, and this, unfortunately, is a fairly stupid example, but it's the only one we've got at the moment, so let's just work with it. if I take the tensor eta, the special relativity the special relativity metric, I plug in some observer's basis vectors into this thing. This, by definition, is eta alpha beta. Suppose I have a different observer who comes along, okay, someone who, we're doing special relativity, so someone who's dashing through the room at 3/4 of the speed of light. I want to know what their components would be. Well, what I do is I just plug into the slots. Let's put bars on the components to denote this other observer. Okay. Do this operation for this other observer's set of basis vectors, and you will get the components that they will measure. Now, one of the reasons why I'm going through this is that last time we talked about how to transform basis vectors between different reference frames. Okay, we know that these guys are just related to one another by a Lorentz transformation matrix. So let's just take this a step further. So this is telling me that the components of the metric in this barred frame, they're going to be what I get when I put into the slots. Okay? Those are the basis vectors in the barred frame using the Lorentz transformation matrix to go from the unbarred frame to the barred frame. Now, remember again, this is one of those places where if you're sort of just becoming comfortable with the index notation, your temptation at this stage is always to go, these are matrices. I should start doing matrix multiplication. Okay? If you set that urge within you aside, you go, no, 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 no. Those are just a set of 16 numbers. Okay? For any particular set of components, I can just pull them out. So because of the linearity of all these slots with this thing, this just becomes those two Lorentz transformation matrices acting on the abstract metric tensor with the unbarred basis vectors in its slots. And this we already know. Okay, this is, by definition, this is just eta mu nu. Repeat this exercise for any tensor you care to write down, any 0n tensor you care to write down. Go through all this kind of manipulation, and you will always find that there's a very simple algorithm for getting the components in, let's call it the barred observer's frame, as converted from the unbarred observer's frame. Essentially, you just hit it with a bunch of Lorentz transform matrices, and as an old professor of mine liked to say at this point, line up the indices. That's really all we're doing. Is we're just going to line up the mu's to convert them to alpha bars. Alpha bar here, mu there, put this guy here. I want to convert my nu into a beta bar, I put my matrix there. Boom. Just line up the indices and we're done. Now, this is, as I kind of emphasized, a fairly stupid example. Because if you take the diagonal of minus 1, 1, 1, 1, and you apply the most god-awful Lorentz transformation you care to write down to it, you do all the matrix manipulation and you line it all up, what you'll end up finding is that this is the diagonal of minus 1, 1, 1, 1 in all frames. Okay? That's actually one of the defining characteristics of the metric of special relativity. If you're working curvilinear coordinates, the metric is always minus 1, 1, 1, 1 to all observers. So, the recipe holds in general. This will hold whenever we are studying tensors from now and from henceforth. Just so happens that this first example we were given is a kind of a dumb one. nonetheless, learn the lesson and overlook the example, and wisdom shall be yours. Okay. I want to spend a few moments talking about a particular subset of tensors, of the 0n tensors, where n equals 1. This is a subset of tensors in general that is known in many textbooks as one forms. For reasons that I will elaborate on in probably 10 or so minutes, these are also sometimes called dual vectors. And just set, if that's sort of making some neurons light up in your head, okay, set that aside for a moment. I want to carefully go through them before I indicate the manner in which there is a duality that is being applied here. So if we go back to the definition of a tensor, this tells us that a one form is a mapping from a single vector to the Lorentz invariant scalars. So using some notation that I will probably only use in this lecture, because we're going to sort of move past this notation pretty soon, let's say a one form. I'm going to denote this with an over tilde on it. So let's say P is a one form. It will have, in this sort of abstract notation, a single slot. So I put the vector A into it. And this then gives me some scalar out. Whoops. Yeah, whatever. Meant to use to the other board. So in my notes, I go through some stuff indicating that this guy it's a linear operation, but that's obvious because it just inherits all the properties from tensors, so I'm not going to go through that. If you want to double check some of the details, they're in the notes that have been posted. Just like with the tensors, I extract components from this thing. By putting my basis vectors inside. So if I take my one form P, and I put in my alpha basis vector, this gives me the alpha component of the one form. Notice it's in the downstairs position. So when one of the reasons why I want to sort of go through this step is it gives me a way to sort of think about how I get what's going on with this scalar that I wrote down on the top board here. So what is this scalar that I get by putting a vector into my one form? So I take this, put my vector in here. I use the fact that I can write my vector using its components and the basis vector. I use linearity to pull this guy out. Whoops. So the scalar that I get by doing this is just the scalar that one gets by contracting the upstairs components that I use to set up my vector with the downstairs components I use to set up my one form. Okay? This is an operation that is called contraction for reasons that I hope are fairly obvious. So let me define a few other characteristics of this thing, and in just a few moments, we'll see what this is good for. OK, Okay, so one of the things I'm going to want to do is change the representation of this thing. So I'm going to want to know how these components transform between different frames of reference. But we've already done that. Okay, we did this using tensors, and this is just a tensor. Okay, so if I change reference frames, if I want to know what the components are according to some BARD observer, I will step through the algebra in my notes, but I think you know where I'm going to go with this. You just take the components in the unbarred frame, line it up, contract it with the correct setup of my Lorentz transformation matrix, boom, line up the indices, and we've got it there. So the last thing which I want to do with this, before I sort of talk a little bit about what this is really good for, is say, I've got these basis vectors that allow me to kind of relate the components of my vectors to the geometric object in a way where I don't have to use a represented by symbol. I actually have an honest to God equal sign. Can I define a similar set of basis 1 forms? What I want to do is define a family of geometric objects and I will denote them with an omega and a tilde. Such that any one form can be written as its components attached to these little basis vectors. Well, the way I'm going to do this is I'm going to exploit the fact that I already know what basis vectors are. So I know, for instance, that if I take my 1 form and I plug in a basis vector, I get this. And so what I want to do is combine this thing which I would like to do with the defining operation of contraction. Okay, so I know P alpha A alpha is what I get when I've got my 1 form and I plug into its slot the vector A. Okay, so let's insist that when I do this, I can write this as P beta omega beta. Now remember, these are the components. This is the actual basis 1 form. So I'm going to stick into my basis 1 form this form of the vector. Okay, I can then use, oh bugger. I can then use the linearity of the tensor nature to pull out that component of A. So what this tells me is this is exactly what I want, provided whatever this geometric object is, it obeys the rule that when I plug basis vectors into it, I get the Kronecker delta back. Okay, now this may all seem really, really trivial right now. And indeed, if you think about this, in terms of just writing down mathematical symbols, this is fairly trivial. Okay, one thing which I want to emphasize is that if you go through and say, well, if I'm working in a basis where this has a time-like component that I'll say is 1 the time-like direction, 0 everywhere else, It has a member of the set that points in the x direction, so it's 0, 1 along x, 0 everywhere else. This then leads to, so as an example, a set of basis objects that a particular observer would write just like so. Okay, and I won't write out the 2 and 3 components. And again, you look at this and you think to yourself, dude, you're just repeating basis vectors. What's the big deal here? Now I'm going to explain the fact that these are sometimes called dual vectors. So if we want to think about this in a language that is reminiscent of linear algebra, if you think of the basis vectors as column vectors, then my basis 1 forms are essentially row vectors. Okay? So these look a lot like my basis vectors. They enter in a dual way. Okay, and so they end up playing, they're going to play an important role in helping us to, whenever I contract two objects together to make some kind of a Lorentz invariant scalar, I'm going to want to only combine objects that have a dual nature like this. That's the only way I can get something sensible out of it. So let me give you an example. Mathematically, this is an equation that I can write down. Okay? No question. If I'm in a particular frame, I've got the components of vector A, I've got the components of vector B, I can multiply their components together, sum them, and square them. So this is mathematically well defined, but plays no role in the physics we are going to talk about this term. Okay, because this is not related to the underlying invariant structure of the manifold that we are working with. So remember I talked about how a manifold is essentially a sufficiently smooth set of points endowed with a metric. Well, the metric is what tells us that this is, mathematically, sure, write it down, but it means nothing. By contrast, of course, this has frame-independent meaning. This is important. So that's the sense in which these P's, this is the sense in which these one forms are often called dual vectors. Okay? It is when they are combined with vectors, they are dual to it in the sense that when they are combined in this appropriate way, we find that they describe the physics. They capture the invariant characteristics of the physics that are important in the theory that we are describing. If I may sort of give one more example that is from a completely different field, but I think helps to sort of illustrate a useful analogy to think about these things. Suppose you are doing quantum mechanics, and I give you two wave functions. So suppose you have a wave function psi of x and another wave function phi of x. If you wanted to, you could multiply them together and integrate over all space. I don't know what you would do with that, but you could. On the other hand, you could take the complex conjugate of one of them, multiply it by the other one, multiply it over all space. And in the notation that you learn about, this is, of course, just the inner product of wave function psi with wave function phi. Okay? Forming the one form, using the one form is akin to selecting an object that has, it allows us to make a mathematical construction similar to the quantum mechanical inner product that we use here. And as we'll see in just a couple of minutes, it's actually really easy to flip back and forth between one forms and vectors. Okay, so better way to sort of move forward with this is rather than talking in terms of these more abstract things, let me give you a good example. So imagine I have some trajectory through space-time. So let's let the t-axis go up. There's my x and y axes. You all can imagine the z-axis. And some observer moves through space-time like so. Last lecture, we talked about a couple of important examples of 4 vectors. And so one, which is germane to the situation, is the 4 velocity of this observer. That just expresses the rate of change of its position in space-time per unit proper time. Okay? And I'll remind you, tau is time as measured along this observer's trajectory. So roughly speaking, not even roughly speaking, exactly speaking, tau is the time that is measured by the clock, by the watt of the person moving along there. Okay? So suppose in addition to this person sort of trundling along through space-time here, suppose space-time is filled with some field phi, which depends on all of my space-time coordinates. The question I want to ask is, what is the rate of change of phi along this observer's trajectory? So if you were working in ordinary Euclidean space, you would basically say, this is easy. So your 3-space intuition, you don't have this proper time to worry about. So you would just say that d phi dt along this trajectory is just what I get when I calculate dx dt, and then look at the x derivative of my field phi, plus dy dt bugger. This is one of those places where getting the difference between a partial and a total derivative right is important. So if you see me do that again, if I don't correct it, yell at me. Okay, so you get this, and then you say, this is nothing more than that particle's velocity dotted into the gradient of the field phi. Okay, it's a directional derivative along the velocity of this trajectory. So generalizing this to space-time, you basically have the same thing going on. Only now, time is a coordinate, so we don't treat time as the independent parameter that describes ticking of clocks as I move along it. I use the proper time of the observer as my independent parameter. And so what I will say is, bugger, I did it again. So the rate at which the field changes per unit of this guy's proper time Okay? Every one of these is a component of the 4 velocity. So now we introduce a little bit of notation. So this derivative, I'm very mad at myself here. Stop doing that, Scott. It's what I get when I contract the 4 velocity against a quantity that's defined by taking the derivative of this field. We're going to be taking derivatives like this a lot. So a little bit of notation being introduced to save us some writing. This is the directional derivative along the trajectory of this body. Now this is a frame-independent scalar. Okay? This is a quantity that all observers will agree on. This is a 4 velocity. We know this is a 4 velocity. These are the components of a 4 vector. So these are the components of a 1 form. Okay? So the generalization of a gradient is an example of a 1 form. So reusing that abstract notation that I gave earlier, I can write, so what way you will sometimes see this is the abstract gradient 1 form of the field phi is represented by the components, the alpha of phi. You will also, in some cases, and I actually have a few notes about lines about this in my notes. Sometimes people will sort of recycle the notation of a gradient that you guys learned about in undergraduate E&M. I urge a little bit of caution with this notation, okay? Because we are going to use this symbol for a derivative to mean something a little bit different in just a couple of lectures. It turns out that the something different reduces to this in the special relativity limit, so there's no harm being done. But just bear in mind, this particular notion of a derivative here is going to sort of change its meaning in a little bit. Another little bit of notation that is sometimes used here, and this is one where unfortunately I think I'm stuck with this notation. One often says, so this idea of taking a derivative along a particular 4 velocity, it comes up a lot. So sometimes what people then do is they define it as the directional gradient along u of the field phi. Okay? So don't worry about this too much. We'll come back to it when it's a little bit more appropriate. I just want to be aware, especially for those of you who might be reading ahead, when you sort of see this. So just think of this as what you get when I am taking a gradient along a velocity u. It basically refers to the gradient 1 form contracted with the 4 vector u. So coming back to, so the last thing I want to do as I talk about this is revisit this notion of 1 forms as being dual to vectors for just a moment. So we've just introduced the gradient as our first example of a 1 form. So the notion of the gradient as a 1 form this gives us a nice way to think about what the basis 1 forms mean. So when I introduced basis 1 forms a few moments ago, it was a purely mathematical definition. I just wanted to have objects such that when I popped in the basis vectors, I got the Kronecker delta back. And, you know, after sort of belaboring the obvious, perhaps for a little bit too long, we essentially got a bunch of 1s and 0s out of it. Now, putting in math all of those words, I did a lot of junk to get that. Okay? But we also know that if I just take the derivative of my coordinate with my coordinate, I'm going to get the Kronecker deltas. Okay? You know, this and this, these are the same thing. So I can think of this operation here as telling me, if I regard this as this kind of abstract form of the gradient applied to the coordinate itself, this is nothing more than my basis 1 forms. So my basis 1 forms are kind of like gradients of my coordinates. Okay, you're sitting here thinking, okay, what the hell does this have to do with anything? So let me combine, set that aside for just a second, and remind you of some pretty important intuition that you probably learned the very first time you learned about the gradient. So imagine I just draw level surfaces of some function in, well, let's just do 2-dimensional space. Okay, so I have some function, h of x and y. Okay? This represents, like, for instance, a height field. Okay, if I'm looking at a topographic map, this might tell me about where things are high and where things are low. Okay, so h of x, y, there might be level surfaces on my map that kind of look like this. There'll be another one that kind of looks like this. And maybe I got something like this. And then something kind of right here. So we know, looking at this thing, that the gradient is very low here and very high here. Let's put this into the language of what we are looking at right now. Okay, let's let delta x be a displacement vector in the xy plane. And dh is going to be my 1 form of my HUD function. Okay? How do I get the change in height as I move along my displacement vector? Well, take my 1 form, plop into its slot delta x, I get something like this. What this is kind of, the thing which I kind of want to emphasize here is we have a lot of geometric intuition about vectors, right? So if I have a delta x, let's say this is my delta x, it lasts for about this long over here. And it lasts, I take that exact same delta x and I apply it over here. I get a very different result because that goes through many more contours on the left side than it does on the right side. And the thing, this is where this duality kind of comes in. And I'm going to put up a couple graphics illustrating this here, is that you should think of the one form as essentially that set of level surfaces. Okay? It's a little confusing. I'm not going to, I mean, I can see a couple blank looks. Maybe even majority of you have kind of blank looks on your faces here. Okay? And that's fine. Okay? So what I kind of want you to regard is that when I'm talking about basis one forms and one forms of functions, they have a very different geometric interpretation, even though you're kind of used to gradient as telling you something about, you know, the direction along which something is changing. Actually, you define that direction, and the thing that you're worried about is sort of how close the different level surfaces are of things. Okay? So coming back to this idea that my basis one forms that I use are essentially just the gradients of the coordinates. So I'm going to put some graphics up on the website, which I've actually scanned out of the textbook by Misner, Thorne, and Wheeler. And what they basically show is if I, let's say this is the time direction, let's say this is my x-axis, and this is my y-axis, your intuition is that the x basis vector will be a little arrow pointing along x. What your intuition should be like for the x basis one form is a series of sheets normal to the x-axis that fill all of space, okay? Spaced 1 unit apart. Filling all of space kind of like that. So here's one example of one of those sheets. And notice the x-axis pierces every one of those things. That's another way in which these are sort of a set of dual functions to the vectors themselves. Okay? This notion, so I'm going to turn to something which is perhaps a little less weird in about 30 seconds. But the one thing which I kind of want to emphasize with this, and again, I'm going to put a couple graphics up that help to illustrate this, and there's some really nice discussion of this. MTW is particularly good for this discussion. This ends up being a really useful notion for capturing how we are going to compute fluxes through particular directions, okay? Because if I want to know the flux of something in the x direction, well, my x basis one form is actually like a sheet that captures everything that flows in the x direction, okay? So it's sort of a mathematical object that's designed for catching fluxes, okay? All right. If this isn't quite gelling with you, that's fine. Okay, this is without a doubt one of the goofier things we're going to talk about in this first introductory period of stuff. This is one of those places where I think it's sort of fair to say, if you're not quite getting what's going on, shut up and calculate works well enough. Okay, it's kind of like, you know, Feynman's mantra on quantum mechanics. Sometimes you just got to say, okay, whatever. Learn the way it goes, and it's kind of like playing a musical instrument. You just sort of strum it and practice it for a while, and it becomes second nature after a while. All right. So to wrap this up, what I want to do, so the last major thing today is I hope I can kind of put a bow on our discussion of tensors. Let's come back to the metric as our original example of a tensor here. So when I give you the metric as an abstract tensor, and I imagine I have filled both slots, I get a Lorentz invariant number. A dot B is what I get when I take this tensor and I put A and B into its slots. Suppose I only fill one of its slots. Well, if I take this, I plug in the vector A, but I leave the other slot blank, well, what I've got is a mathematical object that will take a vector and produce a Lorentz invariant number. That's a one form. So let's do this very carefully and abstractly for a moment. But at this point, we basically have almost all the pieces in place. And so I'm going to kind of tone down some of the formality fairly soon. So let's define a one form, an object that takes a single vector inside of it, as what I get when I take the metric and put that vector in there. If I want to get its components out, well, I know the way I do that is I put the basis vector in there. This guy is symmetric, so I can flip the order of the metric is symmetric, so I can flip the order of these guys. And what this tells me is that my one form component of A is just the vector component of A hit by the components of the metric. In other words, the metric converts vectors into one forms by lowering the indices. Okay, this is an invertible procedure as well. So this metric, I can define eta with indices in the upstairs position by requiring that eta alpha beta contracted with it in the downstairs position gives me the identity back. Incidentally, when you do this, you again find it's got exactly the same matrix representation. So this thing with its indices in the upstairs position is just -1, 1, 1, 1. It will not always be that way, though. Okay? Again, this is just because special relativity in rectilinear coordinates is simple. So I will often call that the inverse metric. And then you shouldn't have a lot of trouble convincing yourself that if I've got a one form, I can make a vector out of it. By a contraction operation. Okay. That now tells me that I have about 16 gajillion, well, actually, it's a countable and finite thing, but I have many ways that I can write down the inner product between two numbers, or excuse me, between two vectors, right? This guy is if you like, you can now regard a vector as being a sort of a function that you put one forms into. These are all the same. These are all equivalent to one another. And actually making a distinction between vector and one form and all that, it's just kind of gotten stupid at this point. Okay? So the distinction among these different objects, the different names, kind of doesn't matter. Okay, and indeed, you sort of look at this. Up till now, we've regarded tensors as being these sort of things that operate on vectors. Okay, but why not regard vectors as things that operate on one forms? What this sort of tells you is that this whole notion of tensors being separate from vectors that I talked about before is kind of silly. So I'm going to revisit the definition of a tensor that I started the lecture off with. Like so. So a new and more complete definition. A tensor of type Mn is a linear mapping of M one forms and N vectors to the Lorentz scalars. In this definition, so we've already introduced 0, 1 tensors. Those are one forms. 1, 0 tensors are vectors. Furthermore, as I kind of emphasized when I wrote this sentence here, the distinction between the slots that operate on vectors and the slots that operate on one forms, it's nice for getting some of the basic foundations laid. This is one of those places where now that the scaffolding is in place, we've had the scaffolding in place for a while, but sort of like this wall of our edifice is pretty steady, so we can kick the scaffolding away. We can sort of lose this distinction. The metric lets us convert the nature of the slots on a tensor. So if I have an Mn tensor, and I use the metric to lower, that means I make it an M minus 1, N plus 1 tensor. So an example would be if I have, make this where it's a little bit easier to read. Let's say I've got a tensor R, mu, beta, gamma, delta, and I lower that first index. Okay, so this went from something that operates on one form and 3 vectors, now it's something that operates on 4 vectors. Likewise, using the inverse matrix, the inverse metric, you can raise and just for completeness, let's write that out. So an example of this would be if I have some tensor S mu beta gamma, and let's say I raise that first index. Okay, you get something like this. Okay, so let's see. In my last couple of minutes, recall I do have to leave a little bit early today because I need to introduce a speaker. But I just want to wrap up one thing kind of quickly. I've spent a bunch of time talking about basis objects. And I'm going to go through this fairly quickly. The notes, if you want to see a few more details, you're welcome to download and look at. They're not really tricky or super critical. We know we have basis objects for vectors, which hopefully you have pretty good intuition about. We have basis objects for one forms, where your intuition is perhaps a little bit more befuddled, but it'll come with time. So you might think, ugh, now I've got 2 index tensors, I've got 3 index tensors, there's a 4 index tensor on the board, Scott's probably going to write a 17 index tensor on the board at some point. Do I need a basis object for every one of those? So in other words, do we need glad that's caught on video. Do I need to be able to say something like the abstract metric tensor is these components times some kind of a 2-index basis object? Okay? Do I need to do something like this? Cutting to the chase, the answer is no. Basis 1 forms and vectors are sufficient. So what we're going to do is abstractly sort of just imagine that if I do have a tensor, I kind of have an outer product. Okay, I have both of the basis objects attached to this thing, and each one is just attached to those 2 slots. Okay, so in this particular case, my 2-index basis 2 form that would go with this thing here, thing with 2 indices on it, I'm just going to regard this as, I'll abstractly write this as just an outer product of the basis 1 forms. Okay? If I ever need a basis object for a tensor like this, I will just regard this as an outer product of these 2 things. So what's going on with that notation? What does this mean? Don't really lose too much sleep about it. It's basically just saying that I have separate objects attached to all of my different indices, and they're kind of coming along here and giving a sense of direction to these things. So for instance, if I have some kind of a tensor, I mean, a great one, which we're going to talk about in just a little bit, is a quantity known as the stress energy tensor. In which I can abstractly think of the tensor as having, I mean, not just abstractly, it will have 2 components, and I can think of it as essentially pointing in 2 different directions at once. Now, we're going to talk about this in a lot more detail in a couple of weeks. Actually, not even a couple of weeks, a couple of lectures. What I'm going to teach you is that the alpha beta component of the stress energy tensor tells me about the flux of 4 momentum component alpha in the beta direction. Okay? And so this is basically saying, you know, when I think of it as the actual object, not just the representation according to some observer, here is the thing that gives me the direction of my 4 velocity, excuse me, my 4 momentum, and here is the direction in which it is flowing. Okay? And, you know, sometimes we will make more complicated objects, and so you might need to sort of imagine. Here's one which I actually wrote down in my notes here. There will be times when we're going to care about a tensor which, at least abstractly, we might need to regard as having this whole set of sort of vomitous basis vectors coming along for the ride here. Okay? And, you know, it is actually fairly important to have all these things that are in place. Where I will just conclude things for today is that the place where it is particularly important to remember that we kind of sometimes almost just implicitly have these things coming along for the ride here it's important when we calculate derivatives. So I gave you guys an example of a sort of a directional derivative for a scalar field that filled all of spacetime. I imagine that there was some trajectory of an observer moving through this. Now imagine it isn't a scalar field that fills all of spacetime, but it's a tensor field. So here's t. Say this is the y direction, this is the x direction. Here's my observer moving through all this thing. And again, I'm going to say that this trajectory is characterized by a floor velocity, dx d tau. And I'm going to imagine that there is some tensor field that fills all of spacetime. When I go and calculate the derivative of this thing, when we're working in special relativity where we are right now, these guys are going to be constant, so it doesn't really matter. But soon we're going to generalize to more complicated geometries, more complicated spacetimes, and the basis objects will themselves vary as I move along the trajectory. And I will need to, in order to have a notion of a derivative that is a properly formed geometric object, I'm going to have to worry about how the basis objects change as I move along the trajectory as well. Okay, so that tends to just make the analysis a little bit more complicated. I have a few notes about this that I will put up onto the web page, but I don't want to go into too much detail beyond that until we actually get into some of the details of these derivatives. So I'm just going to leave it at that for now. So yeah, I'll just say the derivative in principle and quite often in practice it will depend on how these guys vary in space and time. Okay. And let me just say, you guys kind of already know that, because when you studied E&M, you got these somewhat complicated formulas for things like the divergence and curl and stuff like that. And those are essentially because those are sort of notions of derivative where you are taking into account the fact that when you're in a curvilinear coordinate system, your basis vectors are shifting as you move from point to point. Okay? The stuff we're going to get out of this will look a little bit different. And it comes to the fact, as I emphasized in my last lecture, that we are going to tend to use what we call a coordinate basis, whereas when you guys learn this stuff in E&M, you were using what's known as an orthonormal basis. And it does lead to slight differences. There's a mapping between them. Not that hard to figure it out, but we don't need to get into those weeds just now. All right, so I will pick it up from there on Thursday. So I'll begin with a brief recap of everything we did. The primary thing which I really wanted to emphasize more than anything is this board plus this idea that the metric can be used to raise and lower the indices of a tensor. Okay? At this point, talking about vectors, talking about one forms, you know, many of you in a math class probably learned about contravariant vector components and covariant vector components. Once you've got a metric, it's kind of like, who cares? Okay, you can just go from one to the other. And that's why I tend to, almost religiously, I avoid the terms covariant and contravariant, and I just say upstairs and downstairs. Okay, because I can flip back and forth between them, and there's really no physical meaning in them. You have to think carefully about what is physically measurable, and it kind of has nothing to do with whether it's covariant or convariant, upstairs or downstairs. All right, I will end there since I have to go and introduce someone. Okay, great. So at this point, we basically have all of the most important, well, we now have the full understanding of how to work with tensors. I haven't really done too much physics with them at this point, but we've very carefully, one might even argue excessively carefully, laid out this mathematical structure that is going to be, we're going to use it to sort of contain the geometric objects that will describe the physics that we're going to study over the course of the entire semester. So there was a lot of twiddly detail in the preceding lecture, but I would say the two most important things I want you to take out of this is the idea that we now have tensors as a sort of general class of geometric objects which map one forms, or dual vectors if you prefer, a combination of one forms and vectors to the Lorentz invariant real numbers. And further, the distinction between one forms and vectors and what is being mapped to what is kind of not so important, because I can always use the metric to either raise or lower indices on tensors or vectors or one forms in order to convert from one to another. So if I raise an index, if I have a tensor that's got m indices in the upstairs position and n in the downstairs, I raise an index, now I've got m plus 1 upstairs, n minus 1 downstairs. Okay, and likewise, I can lower an index, put one of those ones in the upstairs down to the downstairs. We wanted to go through all that stuff with great care because we're going to need the foundations of that to make a lot of what we talk about later rigorous. It is really overkill for where we're starting, okay, but it's worthwhile to have that sort of scaffolding in place. I'm sick of it, though. So today I'm going to try to do some things that are more physics, okay, because, well, not all of you are necessarily physics students, but I'm a physics professor, and I'm a little tired of doing math. So let's think about, when we're studying physics, generally we are interested in the behavior of bodies and fields. Let's move to the relativity framework. We're looking at behavior of bodies and fields in space-time. So far, if I think about the quantities that we have introduced, and by the way, I apologize for the blackboards. A previous lecturer today used chalk that cannot be erased very well, so they're sort of grayish boards today, unfortunately, but we'll manage. Anyhow, so far, the quantities that we have introduced, oops, that have solid physics content are good for describing particles, individual particles, maybe a handful of them at once. So the two that I want to focus on in particular are the 4 velocity. So if I have a body with a 4 velocity u, a particular Lorentz observer, we'll describe that as having a time-like component gamma, the special relativistic gamma, and a space-like component gamma v. Okay? This is defined such that u dot u equals -1. It is great for describing, it is the tool we use to describe the trajectory of a material body that follows a time-like trajectory through space-time. Notice that its norm is -1. The fact that it's 1 means it's normalized, and the minus tells us that it is time-like. By the way, because this is time-like, the 4 velocity is not going to be a useful tool for us when we want to describe the behavior of light. Okay? If we want to talk about the motion of a photon in our space-time, we can't use a 4 velocity for it. Okay? 4 velocities, the trajectory of a photon is null. Okay? Whatever quantity that is going to describe its trajectory, I take its dot product with itself, I have to get 0. And you can sort of intuitively get a sense of what's going on with that. If I take the way a particular observer interprets these things and says, what would this turn into if v equals c? Well, you have infinity and infinity, right? Because your gammas are diverging there. So it's a singular limit. It doesn't behave well. We will overcome this difficulty. The other quantity that we have used, let me see if I can clean this a little bit better. All right, the other quantity that we have defined, which is good for particles, is the 4 momentum, which is just that 4 velocity multiplied by a rest mass. Okay? so this is defined. You can kind of clearly, by trimming together a bunch of definitions, you have P dot P equals minus m squared. We're actually going to interpret this, though. So if a particular Lorentz observer makes a measurement of this, they will call the time-like component E and the spatial component P. And so you put all these things together, and this tells me that E squared minus magnitude of P squared equals m squared. Notice this is perfectly well behaved for a massless particle. Okay? This is actually going to be the trick by which, when I want to describe the trajectory of photons or of light in a space-time, I can't use 4 velocity, but I can use 4 momentum. Okay? Works perfectly well. You know, it's 0 times a 4 velocity, but if I use this intuition that this thing is diverging when I take the speed of light limit, I sort of, this is a cheat, but I'm basically getting 0 times infinity, and it behaves. Okay? We're going to do it a little bit more rigorously than that, but if you want a little bit of intuition, that's essentially why it works. So the last thing which I will say here is that this is good for m equals 0. Okay? And when you do have m equals 0, it's often convenient to write this as h bar omega. So use the usual formula for the energy of a photon. Let me move this so that people can see. And then I just put a unit vector into the spatial direction that defines the direction in which this is moving. Okay. So this is all fine as far as it goes, but it's kind of restrictive. Okay, we want to do a little bit more with our physics than just worry about the kinematics of individual particles. Okay, there's a lot we can do with that, but you know, one of the things that we like to do when we're studying gravity is to have a description of continuum matter like things that gravitate. Okay, we want to be able to build a description of something like a star, or an exotic star, a neutron star, or something like that. And so just having sort of the behavior of individual particles is not good enough. I want to be able to describe things like fluids. I want to be able to have a continuum that describes things. So what I'm going to start doing today is begin to introduce the mathematical tools that we will use. Pardon me. I seem to have twisted this around myself in a crazy way. We're going to describe the mathematical tools that are useful for dealing with continuous matter rather than just particles. So let's call this more interesting matter. So the simplest continuum form of matter, which we're going to talk about, is, we're going to call it dust. Okay? When you're here at the chalkboard, you kind of can't get away with it, so you have an idea of what it means. Physically, what I mean by dust is that it is a collection of particles that do not interact with each other. Okay? So they sort of pass through each other. There's no pressure that is generated. So they have energy density associated with them. But no interaction. So it's the most boring kind of matter that you like. You can think of it as essentially just particles, but it's a ton of them, and they're sort of smearing out into a continuum. Okay? In particular, one thing I'm going to say is, so I can imagine, like if I take my 2 erasers here, I have a nice dust field in front of me now, which I hopefully is inhaled. And you can sort of think of this thing as sort of a field of little dust elements that are all sort of moving around. If I go in and I track an individual element of that dust, I go in and I make a little cube that's a nanometer on each side, every little element has its own rest frame. Okay? In that cloud, I'm not going to do that again, but as I made that cloud, different elements within the cloud have different rest frames. But for each individual element, I can define a rest frame. So we're going to use the properties of the dust in that rest frame as a way of beginning to sort of normalize and get a grasp on how we're going to describe this. But let me just emphasize again, in a given cloud, different elements may have different rest frames. Okay, but let's suppose that, you know, I clap my erasers, I make my little cloud, and I go and I zoom in on one particular nanometer by nanometer by nanometer chunk of that thing, and I go into the rest frame of that particular little bit of dust. So how am I going to characterize that? So presumably, each particle has its own mass associated with it. Each little element, each little bit of dust that's in that thing has its own mass. We're going to worry about how that comes into the picture a little bit later. Let's just begin by saying one of the things we're going to be interested in knowing is how much dust is there in that little cubic nanometer of dust that's in front of me there. So the first thing we're going to focus on is just counting how many bits of dust are in this element. In particular, I'm going to want to know how many elements per unit volume. In other words, the number density. So I claim that's a good thing for us to get started on. And it looks like they haven't quite poisoned this board as badly. Good. So let's call n sub 0 the number density in the rest frame of that element. Okay, so this will just be some number per unit volume. Okay, so it's a quantity that has dimensions 1 over volume. Now, in the rest frame, you know, like I said, we're going to talk about how I treat the mass associated with each element and how much energy is in that thing a little bit later. There's a few other tools I want to introduce first before I get to there. But in the rest frame, you know, if I'm not worrying about the mass and the energy, this is it. Okay, this is really the only thing I can say about this. So what I'm going to do now is say, okay, well, if I have a general cloud here, you know, as I described when we made this little turbulent cloud of dust in front of us, it was all swirling around and doing its own thing. You're generally not in the rest frame. Okay, so you also want to know how to characterize the dust out of the rest frame. So let's move out of the rest frame. When I do this, two things happen. So first of all, let's continue to focus on, so we've got a particular nanometer cubed of dust that we are looking at here. So you know, we're very attached to that particular thing. So I now boost into a frame where I'm going 3/4 the speed of light or something like that, but I'm going to pay attention to that. I'm very attached to the dust in that little cube, so I'm going to keep myself focused on that. Boosting into frame can't change the total number. So the amount of dust has to be the same, but of course there's going to be a Lorentz contraction, and so the volume will get smaller. So the number in a particular volume stays the same, while the volume Lorentz contracts. And so let's call n the number density in this new frame. This is just going to be the Lorentz gamma times n0. Okay? So again, I'm assuming you're all perfectly fluent with special relativity. So all I did there was say it's going to contract along that direction. The lengths are smaller by a factor of gamma. Therefore, the volume is larger by a factor of gamma. But there's a second thing that happens as well. When I'm in this new frame, there is now a flow associated with the dust. So this will now be flowing through space. In particular, what you can do is define a flux that describes the number of particles crossing unit area in unit time. So let's define n3 vector to be this. And you use a little bit of intuition and just think about the flow of these particles as they kind of go translating past you. This can only be the number density that you measure in that frame times the 3 velocity. Okay? Think about that a little bit. It's very much like when you learn about current density in basic E&M. Notice it's n and not n0 here. So, you look at these two things for a moment or two. Let me just write down one more step. I can write this as gamma n0 v. These are screaming to be put together to make a 4 vector. Okay, they're sort of looking at me and saying, this bit's kind of like, I'm a time-like piece of a 4 vector. Spatial piece, I love you, let's get together. I mean, they clearly are just screaming to go together. And when you do that, you sort of say, let's see what happens here. Two great tastes that taste great together. Okay, that's nice. Let's take advantage of the fact that both of these have a really simple form in terms of the density in the dust zone rest frame. And you look at this and go, holy moly, that is nothing more than the number density times a 4 velocity. Okay? So that's pretty cool. Okay, if I have this stuff in front of me, again, what the heck, this time I'm going to actually do my clap again. So I do this, every little element, I can think of it as having some trajectory through space-time. I can attach a 4 velocity to that. And if I know what the density of dust is in that rest frame, I put it together, now I've got a geometric object that describes this thing. And one of the reasons why this is powerful is geometric objects, as I have emphasized repeatedly, have kind of a geometric meaning that transcends a particular coordinate representation. Another way to think about this is that all observers, I don't care whether you're sort of at rest in this classroom or you've had too much coffee and you're dashing through at 3/4 the speed of light, we all agree on n, capital N vector. Okay? But we choose different ways of splitting space-time into space and time. And so I will have a different n from you. I will have a different nv from you. We all have different ways of splitting this space-time into space and time. And so we have different ways of splitting these two things up. But this is a geometric object we all agree on. It's something that we can hang a lot of our physics on and build frame-independent, powerful geometric representations. So before going on to do a few things with this, let's just explore a couple of the properties of this. All right. So whenever you've got a 4 vector, it's at a certain point you just sort of say to yourself, well, I've got this thing. Let's take the dot product with itself. Why not? So in this case, n dot n equals minus n0 squared. Or, turning this around, this tells you that if someone comes by and goes, psst, here's a number 4 vector, you can figure out density in the rest frame associated with each element by the following operation. So that's nice, okay? In other words, the number density, in a sense, tells you what the normalization of this vector is. A few moments ago, I sort of defined n as being kind of a flux of these things. Okay, it's a flux in the spatial directions. We want to think about flux in a more general kind of way, and so another thing which we're going to do, and this is where one forms are going to play an important role for us. Is a nice systematic way to pick out a flux across a surface. So here's the bit where when I was talking about it in Tuesday's lecture, I was kind of getting the blank stares, and sorry, I'm coming right back to this again. So we're going to sort of harp on this concept a little bit more. So recall, we talked about the fact that if I have a particular coordinate system, okay, I have a particular set of coordinates x alpha that I use to represent space-time. If I make one forms that are the gradients of those coordinates, I can represent them as essentially level surfaces at unit ticks of the coordinate x alpha. Okay? And basically the way to think about it, I kept emphasizing that these one forms are sort of dual, the basis one forms are dual to basis vectors. And if you have this intuition that your basis vector is a little arrow pointing like so, then the thing that is dual to it is a surface that is everywhere but pointing along like so. Okay, that's kind of the way I want you to think about it. And those graphics that are sort of scans from MTW I put on the web give better pictures of that than I'm able to draw. So putting these concepts together, it basically tells me that I can use these basis one forms as a way of defining sort of in an abstract form. So if I want to know the flux of n in the, let's write it this way, in the x alpha direction. So remember the basis one forms, okay, that is, the alpha in that case is not like a coordinate index. It's labeling a particular member of a set. And so what you would do is you would construct this by saying, okay, let's take the beta component of basis one form alpha, contract it like so. And that tells me about the flux, how much of this stuff is flowing in the direction associated with alpha. So this is a tool that we're going to use from time to time. One little thing which I want to emphasize, actually two things I want to emphasize. So if I'm working in an intelligent coordinate system, remember this is basically just the identity matrix, right? And so this ends up being a very simple thing to actually work out. And it sort of says if I want to know the time-light component, then this is 1, the time-light direction, 0 everywhere else. And I just pick out n sub t, okay? In other words, the density itself in that frame. That is the other thing I should want to emphasize. So when you do this, if I pick out the time-light piece of this, this just gives me the 0 component of this thing, which is the density that I measure in this frame. Okay, this is very, very simple in terms of the calculation, but I want you to sort of stop and think about what it means physically. So flux in the time-like direction. What does it mean for a flux to be in the time-like direction, right? If I take my water and actually I'm kind of thirsty, so I want a little bit of flux of water going down my throat. You have an intuition about what that means. Okay, the water is actually flowing in a particular direction. If it's flowing through time, there it goes. Okay, that basically means it's just sitting there. It's not doing anything, but just sort of moving in time, as we all are doing. One time I remember my wife saying about our daughter, she's like, oh, she's growing up so fast. And I was like, she's growing up at 1 second per second. And, you know, that's just the way things go. It's just sitting there and it's living its life at 1 second per second, as we all do. That is density, okay? So we describe the flux of a thing in time as just being its density. That's another way when we do a lot of our calculations and we talk about sort of the flow of things in a time-like direction, that tends to be just the simple density associated with stuff. And then if I did this, if I pulled out the x direction of this thing, I would pull out the x component of velocity times that, and that's sort of the flux of something in the x direction like you are probably used to from other classes. Now, a place where this turns out, so doing it when I'm just using the basis one forms, it's kind of trivial. Bugger, that sucks. More generally, what you can do is define a surface as being, you know, the solution of some scalar function in space-time. So let's say I do something like psi of t, x, y equals a constant. Okay, this is very abstract, so let me just make it a little bit more concrete. Suppose my function psi were square root of x squared plus y squared plus z squared, and my constant was 5. Okay, well then my scalar field will be picking out a sphere of radius 5. Okay, you can make it a little bit more complicated than that, and people often do. You can define the unit 1 form that is associated with the normal to this thing. Or rather, it's the 1 form associated with the surface. If you translate this to a vector, okay, you raise the index and think of it as a vector, it would be the vector normal to the surface. You might need to normalize it. Let's imagine that we normalize this thing. And then we would just need to contract it along this, and that tells me about the flux through this particular surface. Okay? So this is one of the things that this sort of idea of one form as being level surfaces, it tends to be useful for things like that. We're going to come back to this, a similar sort of picture in just a moment, because I'm about to start talking about integration. Okay, in prep for that discussion, so now that I'm talking about things a little bit more complicated than just the kinematics of simple particles, we're going to want to have some laws, and we're going to want to have geometric ways of describing those laws that essentially act as constraints on what those particles can do. Okay, so the form in which we're going to express them, we're going to tend to put things into the form of conservation laws. So suppose here's my little element that's got dust in it, and it's embedded in an environment with a bunch of dust around it. And over some time interval, some dust flows in, some dust flows out. The density can go up, the density can go down, the total number, you know, it may vary depending on how things are flying. The spatial flux out of the sides must come and I'm going to say is the flux out. So let's say that that comes at the expense of the density of dust already there. Okay, and so if you were to just to intuitively write down what kind of a conservation law you would expect to see, you would write it as something like this, based on simple Euclidean intuition. Okay, what's kind of nice, you look at that for a second and you go, ooh, if I think about this as being the time component of my 4 vector, this is the space component of my 4 vector, this has a very obvious form when I write it in a sort of a geometric framework. This whole thing can be written as conservation law that looks like this. Okay? So I'll remind you, d sub alpha equals d by dx alpha. I'm going to talk a little bit about some of the derivatives a little bit later because there are a few subtle points that can get introduced. But for now, you just know that d downstairs t is d by dt. D downstairs x is d by dx. D by downstairs y, etc. Okay? So this is really nice. One thing which I want to emphasize, again, coming back to what I said over there just sort of just a moment ago, when I write down this conservation law, I'm assuming that someone has defined what time means and someone has defined what space means. This is a form that's covariant, right? We can, all observers agree that this sort of goes together. When they actually make their own coordinate systems, they're going to have their own time coordinate and their own x coordinate, but they're all going to be sort of different flavors, just different ways of instantiating what this is. Now, pardon me for just one moment. We are at depending on the way the pace of the course, we're about to sort of switch over to a different set of lecture notes. I just want to make sure I smoothly go from one to the other. Okay, so in many of your physics classes, you have learned when you get a conservation law, both a differential form like this, the rate of change of n in a box is related to the amount of n flowing out of that box, its sides, and you also learn an integral form of the conservation law. So without proof, let me just say that it should be intuitively clear that what I've written down over here is equivalent to okay, so it looks like this. You know what? Let me just fix up my notation a little bit. I call this lowercase n. Okay. A few symbols that I've introduced here. So V3 is some volume in three-dimensional space. And dV like this is a symbol that means the boundary of that 3 volume. Okay, and that's basically, it's a form of Gauss's law. That's what I've written down there. Okay, so you've all seen things like that. Again, let me emphasize that when I write down a formula like that, I can only do that having assumed a particular Lorentz frame. Okay? That T is the T of some observer. That volume is the volume of that particular observer who is using T. Okay? You jump into a different Lorentz frame, their volumes will not be the same. Their times will not be the same. I'm going to mix some coordinates up. So an integral form like this, as I've written it there, only works in one given Lorentz frame. Nonetheless, we are going to find it useful even though in some sense when you do it in integral form like this, you're picking out, you're saying things sort of in the framework of some particular observer. Sometimes you want to know in the framework of some particular observer. Could be you, right? I mean, you might care about these sorts of things. And that's good. But the way I've written it here, first of all, it's kind of in language that, it's in a mathematical formulation that's not easy to generalize as I take things up to higher dimensions, okay? And so what I would like to do is think about how to step up a formulation like this in such a way that things are put into as frame-independent a language as is possible, and that will generalize forward when we start looking at more complicated geometries, and this geometry of special relativity. So I want to spend the next roughly 10 or 15 minutes talking about volumes and volume integrals. And my goal here is to try to, I'm going to start by just doing stuff that comes from the Journal of Duh, stuff you have seen over and over and over again. But I want to re-express it using a mathematical formulation that maybe you'll have seen all the symbols, but perhaps not used in quite this way. And then it'll carry forward in a framework that generalizes in a very useful way for us. So let's begin with just simple 3D space. So I'm going to begin in 3D, and I'm going to consider a parallelepiped. Got it right. Whose sides are a set of vectors. So there are 3 vectors, A, B, and C. Okay, so here is vector A. This one going into the board is vector B. And this one going up here is vector C. Okay, so those are my 3 vectors. And if I sort of go draw the ghost legs associated with these things. Okay. Yeah. It's a little better. So these 3 vectors define a particular volume. And you guys have probably all seen, you have 3 vectors. You can define a volume associated with this. A really easy way to get that volume, given those 3 vectors, is to take A and dot it into the cross product of B and C. This is a quantity which is cyclic. So if you prefer, you can write it as B dotted into C cross A, or C dotted into A cross B. That can be expressed as a determinant, or you guys can look at my notes to see the determinant written out if you like, but it's not that interesting because I'm not going to use it very much. An equivalent way of writing all that is to use the Levi-Civita symbol. So that 3 volume is given by epsilon ijk, ai, bj, ck, where I'll remind you, epsilon ijk equals +1 if I equals 1, j equals 2, k equals 3, and even permutations. Even permutations means I swap 2 pairs of indices. So 1, 2, 3, 2, 3, 1, 3, 1, 2. Those all give me +1. It gives me -1 for any odd permutations of those. So 1, 3, 2, 2, 1, 3, etc. Those will all give me -1. And it's 0 if any index is repeated. So you probably have all seen things like this before. This is fairly basic vector geometry. We are going to regard the Levi-Civita symbol as the components of a 0-3 tensor. Okay, bear in mind for just a moment here, I'm working only in, sorry, I just ran out of good chalk. I'm only working in 3 space. So my tensor definition is slightly different. Okay, it's not going to be a set of things that maps to Lorentz invariant, but it's going to be invariant with respect to things like rotations and translations in 3-dimensional space. So I'm going to regard these as the components of a 0-3 tensor that basically takes in vectors and spits out the volume associated with the element whose sides are, whose edges rather, are bounded by those vectors. Okay, so I could sort of say in this sort of abstract form I wrote down earlier, imagine a bold-faced epsilon, which is my volume tensor. I put these slots into it, and voila, I get the volume out of it. Now, with that in mind, remember some of the games that we played with tensors in the previous lecture. So if I, when I was talking about space-time tensors, if I filled up all of their slots, I got out a Lorentz invariant number. In this case, I'm in 3 space, so I fill up all its slots. I get a invariant number in this 3 space. Suppose I only put in 2 vectors. So suppose I do something like I plug in, let's leave the first slot blank, and I put in vectors B and C. Okay, well, writing this out in component form, I know this is epsilon ijk, bj, ck. That's just B cross C, right? Which has, that's the area spanned by the side that is B cross C. And you guys have learned in other classes that you have an extra index left over, so it's a vector that has a direction associated with, so it's sort of an oriented surface. We put the index in the downstairs position, so we're actually going to think about this as a 1 form corresponding to the side whose edges are B and C. So let's call this side 1 form sigma. This is a 1 form whose magnitude is the area of the side spanned by the vectors B and C. And although I can kind of still tell it hasn't quite gelled yet, it's useful to think of 1 forms as being associated with surfaces. Well, guess what? This is the side of a parallelepiped. That's a surface. Okay? So it's actually kind of holds together. All right. So using all of this, if I wanted to write down how to do something like Gauss's theorem, this kind of geometric language. And again, let me emphasize, this is very much in the spirit right now of mosquito with a sledgehammer. Okay, we don't need all this sort of stuff, but we're about to step up to something a little bit more complicated. So what you would do is say, okay, well, I know Gauss's theorem. I pick a particular 3-volume. I say the divergence of some vector field integrated over that volume is given by integrating the flux of that vector over the surface of this thing. So what you might want to do then at this point is say, oh, okay, well, what I'm going to do then is say that my volume, whoops, pardon me a second. First thing I'll do is define a differential triple. I'll define some x1 that points along one direction I care about, an x2, and an x3. And then I will say dv equals epsilon ijk, dx1i, dx2j, dx3k. I can likewise define a one form associated with my area element, as I have done over here. I'm not going to actually write this out. The key thing which I want to say is you have all the pieces. You put all these things together, and you can sort of define this thing. It's now very easy for you to prove Gauss's theorem using these kind of ingredients. What I want to move on to, so there's a few more details in my notes. It's not super difficult or interesting to go through this. What I want to now start doing is generalize all these ideas to the way we're going to approach them in space-time. Basically, we're going to do exactly the same kind of operations that I just did in space, three-dimensional space, but I'm going to put an extra index on things, and I'm going to do all of my quantities in space-time. Okay? So imagine a parallelepiped with sides A, B, C, and D. 4 dimensions, so it's going to point along 4 different, these can be mutually orthogonal. I'm going to define the invariant 4-volume associated with these things. Like so. Where now my 4-index Levi-Civita is defined such that epsilon 0, 1, 2, 3 equals +1. If I do an odd permutation of those, I exchange one pair of them. Epsilon 1, 0, 2, 3. This equals -1. If I repeat any index, I get 0. Okay, and likewise, all even permutations of this give me +1. All odd permutations of this give me -1. Or likewise, just do even permutations of this one. So that is how I'm going to generalize my Levi-Civita symbol. It's a perfectly, as they say on The Simpsons, it's a perfectly cromulent object. I'm going to need to talk about the area associated with the faces of each of these things. So what is the area of the face of a 4-volume? It's a 3-volume. So you can define a one form that tells me about the, you can either call it the 3 volume or the 4 area. Knock yourselves out as to how you want to call it. And it's sort of the obvious generalization. Let's say I leave off I leave off edge A. I want to get something like this. I do my sort of similar exercise of defining in this case, it'll be a differential quartet associated with directions 0, 1, 2, and 3. And so by going through a procedure very similar to this, you get a generalization of Gauss's theorem. Says that if I integrate the space-time divergence of some 4 vector over a 4-dimensional volume, it looks like what I get when I sum up the flux of that guy over all of the little faces. So I'm not going to step through the proof of that. It's fairly elementary, okay, and it's just, basically it's just like proofs of Gauss's law that you have seen elsewhere, but with an extra dimension attached to it, okay? Really nothing new that's going on here. The thing which is new is, this is now being done in an additional direction, an additional dimension. And where this tends to be useful is when there is some kind of a conservation law that tells you something about this left-hand side here. So the whole starting point of this discussion was I wrote down on intuitive grounds that the rate of change of the total amount of, so what I did was I had an integral of dust density over a 3 volume, and I said d by dt of that was balanced by the flux through the surfaces on the edge of that 3 volume. That is as I argue, that's an observer-dependent statement because you have chosen a particular time, you have chosen a particular space to make those volumes. This, on the other hand, so let's switch my general function, my general vector field v to the n that we started this discussion off with. So this guy whoops, let me write it the way I wrote it over there. d4x over some 4 volume. This must be 0 because we are going to require that this thing be, so if my number density is conserved, this must be 0. So this tells me that when I do this flux integral, it's going to have to be 0. Let me now break this integral up and actually write this into a form that is a little closer to the way that you may have seen something like this before. So what I want to do is actually zoom in and think about the 4-dimensional volume that I'm doing this integral over, okay? So I'm just going to do a 2-dimensional cut of it here on the blackboard. Let's let the time axis go up. And let's define the edges of my volumes to be T1 and T2. X-axis going across here. Boundaries are X1 and X2. Okay, so here is my V4. And every face here is an example of my boundary of D4. Okay, of course, there's one over here as well, and over here. So if I were to do the top line here, I know that's got to get me 0. So I'm going to take advantage of this and say, let's just look at what happens when I do the integral of the flux of this thing across the many different faces. So in a four-dimensional parallelepiped, an n-dimensional parallelepiped has 2 n faces. So there'll be 8 integrals we need to do. They're pretty obvious, though, so I'm just going to write down a handful of them. Okay, so integral over all those faces, n alpha d sigma alpha. So what I'm going to do now is say, okay, let's evaluate this on the face that is at t equals t2. So when I do this, I'm going to get n0 dx dy dz. Let's do next the contribution at moment. Actually, let me move this over because I want a little bit more room. I also do one on the slice t equals t1. When I do this, though, in the same way that when you guys do fluxes in three-dimensional space, you get a sign associated with the orientation of these things, because the Levi-Civita symbol here has sort of a right-hand rule built into it, right? And so when I do it for the side that is on the future side of the box, I'm going to get a plus sign. Do all the analysis carefully. On the side that's on the past side of the box, you get a minus sign. Then I'm going to do it. I'll pick out the component n1. And I'm going to do this along the face that's at x equals x1. Sorry, this is supposed to be x2. Okay, you can write down 4 other integrals according to the, when you do the y side and the z side that I have not drawn. Okay, what I'm going to do now is imagine that this box gets very small in the time-like direction. So let's let t2 go to t1 plus dt. And I'm going to do this and then rearrange things a little bit. Again, apologies, I'm eating chalk here. So I'm going to rearrange this integral so that it's of the form, this side's being evaluated at t1 plus t2. So I'm going to rearrange stuff so that I can then write, hang on just one moment. How did I do this? Oh. Apologies. This whole thing, of course, equals 0. Okay, I was just looking over my notes and went, it was a magic sign flip. I was just looking at it and going, where the hell did that come from? Okay, so I left off my equals 0 there. I'm basically moving a bunch of terms to the other side. So now I'm integrating this over the face at x2. Now I do an integral over the face at x1. And then I'm not drawing in a bunch of faces along y2 and y1, z1 and z2. Divide both sides by dt. Take the limit of dt going to 0. What is this? This is the derivative of the volume integral of n0. Let's just write that out explicitly. So if I've got integral t1 plus d2, excuse me, t1 plus dt, and 0 dx, dy, dz, minus integral at t1. All this divided by dt, take the limit as dt goes to 0. That becomes this. That I is a bad erasure. My apologies. What do I get for the other term? Well, when I divide out that dt, I am just left with the flux of the spatial component of the number vector n through all 6 sides at moment t, or t1. And at last, so I will wrap things up in just a moment here. What this finally leads us to is that this fully covariant form that I have at the top there this becomes terrible D's. Whoops. So in the language that you probably learned about it in an earlier class, you can think of this as the area element of each side. These are completely equivalent to one another after you have chosen a particular Lorentz frame and invoked this 4-dimensional analog of Gauss's law. So that was a lot to take. But I wanted to do it for this one particularly, to be blunt, this was a particularly simple example. Because, okay, so right now the only matter that I've introduced beyond sort of particle kinematics is dust. And dust is actually surprisingly important. Okay, when we actually get to cosmology, there are essentially 2 forms of matter that we consider when we study cosmology. And one of them is dust. Okay? In cosmological situations, a dust particle is basically a galaxy, or even like a cluster of galaxies. Okay? We're thinking big. And it's not trivial to do this. But we are soon going to need to introduce mathematical tools that are a little better for describing things like fluids and stuff like that. And when we do that, we are at last going to have things like conservation of energy and conservation of momentum. It will be really easy to write down a differential conservation law that describes conservation of both energy and momentum using that mathematical object. Via a process very similar to what I just did here, we can then turn this into integrals that describe how energy is conserved in a particular volume where things may be flowing into or flowing out of it, and how momentum is conserved per unit volume as things flow into it and flow out of it. Okay, I'm not going to go through that in detail on the board, but having done this, I have some notes that I'm going to post to the website that describe this, and that will be the way we sort of communicate this, and we're going to take advantage. To be blunt, we will mostly just use this differential form. We'll use the fact there's a particular mathematical object whose divergence-like derivative there is equal to 0. Okay, we have a few minutes left, and we've ended early a few times, so I'd like to take advantage of this to switch gears a little bit and talk about another important 4 vector that plays some role in physics and allows me to introduce a few other very useful tricks that we will often take advantage of at various points in this class. I forgot there's a straw. When you tip it, the straw doesn't work. Anyway, so the next example of stuff that we will occasionally talk about is an electric current. So switching gears very, very much now. So we will describe this as a 4 vector whose time-like component is the charge density as seen by some observer, and whose spatial component is the current density as seen by that observer. Bear in mind, you might look at this and twitch a little bit because the units look wrong. Don't forget C equals 1. Okay? So if you use this in other systems of units, sometimes we call this component charge density times C. So you guys have all, you know what, let me just go ahead and write it out. So a couple properties about this are important and interesting. One is that the current and the charge density obey a continuity equation. We can think of it as a conservation of charge. It's expressed, so in elementary E and M, you guys all presumably learned that the rate of change of charge density is related to the divergence of the current density. Well, this is exactly the same as saying that the space-time divergence of the current 4 vector is equal to 0. This is really useful for us, and indeed, bearing this in mind, we find that if we want to express Maxwell's equations in a covariant way, we can do so such that this is built in automatically. So skipping over a few sets of things in my notes, we have found that electric fields and magnetic fields are inconvenient objects to describe using geometric objects that are appropriate for space-time. Okay? If I want a geometric object that is appropriate for space-time, the first thing you think of is a 4 vector. A 4 vector has 4 components. E fields and B fields have a total of 6 components among them. Okay? So what are you going to do? Have 2 4 vectors and just sort of ignore 2 of the components? That seems sketchy. So you think, you know what? Why don't we make a tensor? Ah, crap. A tensor has 16 components. That doesn't seem right. Then you go, ooh, I can make it symmetric. If you have a symmetric 4 by 4 tensor, well, that basically means that the number of independent numbers that go into this thing, you have 4 down the diagonal, And then you count the number that are off the diagonal, you have 6. Okay, there's 16 in total, but the ones that are off the diagonal are equal to one another. So you have 4 on diagonal, 6 off. Too many. So you say, well, what about anti-symmetric? If I have an anti-symmetric object, that means that component F alpha beta is the negative of component F beta alpha. When you do that, that forces you to the conclusion that there are, in fact, actually only 6 independent numbers in that thing. The diagonal has to be 0, okay, because set beta equal to alpha here, F alpha alpha equals minus F alpha alpha. That only works if that component is equal to 0. So the diagonal becomes 0. And only the 6 off diagonals survive. And then you go, holy crap, 6. That's exactly what I need to have a geometric object that cleanly holds the 3 independent electric field components and the 3 independent magnetic field components. So many of you have seen all this. Okay, if this isn't familiar to you, take a look in a book like Griffiths or something like that. It kind of goes through this. The punchline is that what you find is that the electric and magnetic field is very nicely represented by this antisymmetric 2-index object whose components, in the units that we are using, are filled with the E and the B like so. Okay, last semester I had these memorized, but I have totally forgotten them. Okay, so this is a geometric object that, whoops. Anyone know why I just said whoops and had to put a dot on that there? Point is that electric and magnetic fields look different to different observers. This is its representation according to one particular Lorentz observer. Okay, so it's important to get that right. So in terms of this, so you're all familiar with the 4 Maxwell's equations. They turn out to be equivalent to, so if you take a divergence of this F, it is, depending on your unit, some of you might want to put mu zeros in there and things like that. Basically, I'm setting everything that I can never remember to 1. The divergence of that thing, by the way, has to be the divergence on the 2nd index, becomes the current density. This will actually only give you half of the Maxwell's equations. The other half, what you do is you lower these 2 indices. And there's this sort of cyclic permutation of derivatives. They give you these. And so you put these 2 things together, you apply it to this form I've written out here, and you will reproduce Maxwell's equations as they are presented in textbooks like Purcell and Griffiths. The thing which I want to emphasize here is this form that we've got is written in such a way that the conservation of source is built into it. Okay, this sort of geometric language requires that J mu have no divergence. Okay, and let me just show you can do this. All you need to know is that F is an antisymmetric tensor. You don't need to know anything about the properties of the E and the B field. So let's just try it. let's look at the divergence of the current. So I'm going to do 4 pi d mu of j mu. So I'm going to take a mu derivative of this. Now, bear in mind, mu and nu, I'm using Einstein's summation convention, they are dummy indices. So I can relabel them. Okay, I can change them. I can change mu to an alpha, nu to a beta, or I can just change mu to nu, nu to mu. So this, as long as I do it consistently on all objects that have those things, this is the exact same thing. But I also know that this tensor is antisymmetric. So if I switch these guys back, I get a minus sign. Okay? Antisymmetry. What happens if I switch the order of the derivatives? Okay? Does it matter whether I take the x derivative first and then the y derivative, or the y derivative and then the x derivative? Partial derivatives commute with each other, right? They are perfectly symmetric. So this so what I've got is d mu d nu of f mu nu is minus d mu d nu of f mu nu, and that only works if the whole thing is 0. What I just did is I actually just invoked a trick that we are going to use many times. And the one reason why this is this is a bit of a tangent, or more than a tangent, 150-degree turn from what I've been discussing before. But I wanted to make sure you saw this little trick. Whenever I have an object that is antisymmetric in its indices, and I contract it with an object that is symmetric in its indices, you just get 0. Okay? You can go through the little exercise if you're sort of don't feel fluent in this yet. You can do the exercise I just did up there again over. Take advantage of dummy indices. Swap one, work in the antisymmetry. Swap the other, work in the symmetry. Boom, you will necessarily prove that you've got 0. So I lay this out here because there's going to be several times later in the course where I'm going to get to a particular calculation, and there's going to be some god-awful mess. We're going to look at it and go, oh, this is horrible, and then go, wait, symmetry, antisymmetry, boom, we just killed 13 terms. Tricks are fun, okay? So I am going to stop there for today. There's another sort of symmetry, antisymmetry thing which allows you to sort of, if you apply it to the equation of motion of a charge in an electromagnetic field, it sort of just shows you that that equation of motion builds in the fact that in space-time, the acceleration is always orthogonal to the floor velocity. I won't do it in class. It is on page 6 of the notes that I'm about to post up. We will pick up next time. We'll begin by talking about the stress energy tensor. All right, so welcome back. We've all had a little bit of a break. Before I get into, I go over my quick recap. You've hopefully all seen the announcements that we're going to delay the due date of the next problem set until Tuesday. That's in part because some of the material that appears on it is what we're going to talk about in today's lecture. So I want to make sure you've at least seen a lecture on all the topics before you try to do some of the problems on it. In truth, you could probably, based on things I talked about in the previous lecture, you could probably deduce a lot of what you need to do, but still it's good to go over it a little bit more methodically. Anything else I want to say? Yeah, so then the next problem set will be posted a week from, is that right? Yeah, I think it'll be posted a week from today. All right, so let me just get back to what we were talking about last time. So I began introducing some geometric concepts and some quantities that we use to describe matter. We've done a lot of things so far that's appropriate for describing kind of the kinematics of particles, but that's rather restrictive. Okay, we want to talk about a broader class of things than that. And I began by introducing something which is, again, fairly simple, but it's a useful tool for beginning to think about how we are going to mathematically categorize certain important types of matter. Pardon me while I put some of my notes away. Also, pardon me, I'm recovering from I caught a terrible cold over the long weekend, and I'm coughing incessantly, so I will be occasionally sucking on a cough drop. All right, so I introduced this quantity called the number 4 vector, and that is given by, imagine you have sort of, it's best thinking about this in the context of something like dust. So you have some kind of non-interacting little agglomeration of tiny particles. And in the rest frame of an element of this dust, so imagine you go into the, well, I'm going to define the rest frame of that element by saying, imagine you've got a cubic nanometer of it or something like that. And you go into the frame where everything in that cubic nanometer is, on average, at rest. We'll call n sub 0 the rest density. Okay, so I forgot to write that down. So that's the rest density, the rest, pardon me, number density. So I go into that rest frame. That tells me how many little dust particles there are per cubic volume, or per element of volume. Multiply that by the 4 vector that, assuming the 4 velocity describing that element, and we're going to call that capital N. So that's a vector that describes, its components describe the number density in some other frame of reference, in any frame of reference, and the flux, telling me about how those dust particles flow from one element to another. So we spent a little bit of time talking about how to define volume elements in a covariant fashion. I'm not going to go through that, but part of the punchline of doing that is that we're going to define a sort of what I call a covariant formulation of conservation of number. It's going to be the space-time divergence of that vector is equal to 0. Okay, that holds, this equation holds in all frames of reference. If I choose a particular frame of reference, in other words, I define a particular time, I define a particular set of spatial coordinates, I can then break this up and say that this is equivalent to saying that the time derivative of the t component of that plus the spatial divergence of the spatial components of that, they sum to 0. I can also take this thing and integrate over a, oops, it would help to have an element defined here. I integrate this over a 4-dimensional volume, and by my conservation law, I must get 0 when I do that. Again, having chosen a particular frame, defined what time means, defined what space means, I can then split this out into a statement that the time derivative of the volume integral of the time component of this thing is balanced by the flux of the number across the boundaries of a particular 3 volume. Okay? And I'll remind you this notation, this sort of delta V3 means the boundaries of the V3 that's used under this integral. Okay, so we talked a little bit about a few other 4 vectors that are used. In particular, I introduced some stuff that we use in electricity and magnetism. But I want to switch gears. Okay, in particular, I want to introduce and discuss in some detail one of the most important tensors we are going to use all term. So I motivated this by saying, imagine, I have a cloud of dust, and I won't recreate one because I'm getting over a cold and I don't want to breathe chalk dust. So imagine I make a little cloud of these things here. So far, we've characterized this thing by just counting the number of dust particles that are in there. But that's not all there is to it, right? That dust has other properties. And so the next thing which I would like to do is let's consider the energy and the momentum of every particle of dust in that cloud. Okay, so let's just imagine, again, we're going to start with something simple, and then we'll kind of walk up from there to a more generic situation. Let's imagine that my cloud consists of particles that are all identical, and each dust particle has the same rest mass. So suppose this guy has a rest mass m. So one of the things which I might want to do is, in addition to characterizing this dust by saying that the number density, excuse me, in addition to saying that the number density in a particular frame is n or n0, let's go into the rest frame of this thing. I might be interested in knowing about the rest energy density. So I'm going to denote the rest energy density by rho sub 0. Each particle has a rest energy of m. Remember, c is equal to 1, so mc squared if you want to hold to the formula that we've all known and loved since we were babies. So that's the rest energy. And then how many, if I want to get the rest energy density, I count up the number in each volume, or the number per unit volume. So that's m times n0. So that's the rest energy density of this thing. Great. Let's now ask, okay, so that's what it looks like in the rest frame of this dust element. Let's imagine that I now bop into a frame that is moving with some speed relative to this rest frame. In this frame, the energy density, I'm not going to say rest energy density because I'm no longer in the rest frame, but the energy density in this frame which I will denote by rho without the subscript 0, it's going to be the energy of each particle. So that's gamma times m. And the volume is going to be length, it's going to be a little bit larger. Sorry, the volume is smaller, right? So because of a length contraction. And so this guy actually gets boosted up to gamma n0. So in this frame, the energy density is larger than the rest energy, than the rest energy density, with a gamma squared factor. Okay? Straightforward algebra, but I want you to stop and think about what that's telling us. If this rho were a component of a 4 vector, is there any way I could get a gamma squared out of this thing by bopping between reference frames? No, right? When I do that, it's linear in the Lorentz transformation matrix. There's no way with a linear transformation that I would pick up 2 powers of gamma. This is not how you guys are probably all used to from Newtonian physics of thinking of energy density as a scalar. This is not a Lorentz scalar. Okay? A scalar is the same in all frames of reference. So this is a different quantity. So it's neither a 4-vector component nor a scalar. Okay, it's got 2 of those things, so it's not going to surprise you that what's actually going on here is we are picking out, what we've done here is we've picked out a particular component of a tensor. But let's think a little bit more methodically about what tensor that must be. So when I originally wrote down my rho 0 here, I sort of just argued on physical grounds that it is, it's the energy of every particle times the number of particles per unit volume of that thing. Well, the energy that I use in this thing, doing it in both the rest frame and in the other frame, those are the time-like components of a particular 4 vector. Okay? So we assembled rho by combining energy, which is the time-like component of the form momentum, with number density, which is the time-like component of the number vector that I just recapped a few minutes ago. So those are two time-like components of 4 vectors here. So that rho is something like, well, let's put it this way. I can write this as PT NT, which tells me that it belongs to a tensor. So let's define this as some TT of a tensor that I've not carefully introduced yet. There is some underlying tensor that we have built by looking at there's various names for this. We'll call it the tensor product of 2 different 4 vectors. So if I write this in the kind of abstract tensor notation that I've used occasionally, in some of your textbooks, this will be written with a bold-faced capital T. I will use a double overline for this. We might say that this T is the tensor product of the number vector with the form momentum. Okay? Now, the number vector is itself just n0 times the 4 velocity. And my momentum, since all the particles I'm assuming are the same, is just the rest mass times the 4 momentum. This thing actually looks kind of like the 4 velocity times the 4 velocity with a prefactor. And that prefactor is nothing more than the rest density. Okay, so another way to say this is that if I make my cloud of dust, and I go in and I look at its, every little element in it, I take the rest energy density of every element in that dust. I construct the tensor that comes from making the tensor product of the 4 velocity of that dust with itself. That is what this geometric object is equal to. If you want to write this in index notation, which is how we will write it 99.8% of the time, we would say that component alpha beta of this quantity T is that rest density times U alpha U beta. So this is, in terms of the physics we're going to do this term, this is perhaps the most important quantity that we're going to talk about. So it's worth understanding what this thing is really telling us. So if I want to get these components, the alpha beta, out of this thing from this sort of abstract notation of the tensor, so I'll remind you that we can do this by taking the tensor and plugging into its slots the basis 1 forms, which tell me something about basis 1 forms are really useful for sort of measuring fluxes across in a particular direction. And in fact, this quantity has the geometric interpretation. Think of this as the flux of momentum component alpha in the beta direction. Okay, so if we look at this component by component, it's worth doing that. So let's do the TT or 0, 0 component. Okay, so this is the one we've already done. This is just rho 0 ut ut, which is rho in that thing. According to the words I've written down here, this is the flux of pt in the t direction. Okay, so pt tells me about energy. The flux of energy in the energy direction refers to, so here's my water flowing in the time-like direction. Just sitting there apparently doing nothing, but no, it's moving through time. This is energy flowing through time. It's energy density. All sort of locked up in stable equilibrium here. But if somebody comes in someday with a nice cup of anti-water and combines them, we get to have all that energy released, and we can enjoy that for a few femtoseconds before we evaporate. Let's look at the other components. So T0I, okay, you can take the definition and plug it in terms of the components. It's obviously UT times UI. Let's still use the definition by words. So this is the flux of P sub t in the xi direction. Okay, so this is talking about energy moving in a particular direction. This is nothing more than energy flux. Okay, energy sort of flux the way you're used to thinking about it, not flowing through time, but throwing through space. Now T0I, this is the flux of momentum component I in the t direction. So this tells me about momentum density. Okay, so if I have this stuff flowing, okay, there's some momentum associated with that flow. You can count up the amount of mass in every little volume, divide by that volume, take some ratios. That is the density of momentum. And finally, this last one, flux of pi direction. There's really no great wisdom for that. This is nothing more than momentum flux. If I have a bucket of water and things are sort of sloshing around, there's some momentum moving, and the whole assembly is moving in some direction, we can get a flow of momentum going in kind of a non-normal direction. Sometimes it goes in a normal direction. It might be moving along with its flow. I'm going to talk about that in a few moments when I talk about a few different kinds of stress energy tensors. The key thing which I want you to be aware of is that under the hood of this thing, we're going to talk about different kinds of stress energy tensors for a little later in this class. But this basic interpretation of the way to think about the different components, it holds for all of them. Okay? So this is good intuition to have. One thing which is worth noting is, if you actually, let's take the form of the stress energy tensor that corresponds to the dust. Okay, so I'm going to write out all four of my components. I've already given you T00. T0I, I can write that as gamma squared rho 0 VI. T0I equals gamma squared rho 0 VI. And this guy is gamma squared rho 0 VI VJ. There's two elements of symmetry here which I want to emphasize. Notice energy density and momentum flux. Sorry. Energy flux and momentum density. Those words are important. Energy flux and momentum density, they're exactly the same. Okay? That is actually true in all physics, okay? It's clouded by the fact, though, that in most units that we measure things in, we don't typically use speed of light equal to 1. So when you look at these kind of quantities in the physics that you are more used to, you would find your energy flux and your momentum density will have different units, okay? Because you'll have factors of c that come into there that convert from one momentum and energy and time flow and space flow. Also, you don't usually include rest mass and rest energy in the energy flows and momentum densities that you've probably been familiar with in the past. Okay? So it's when we do relativity and we set the speed of light equal to 1 that this symmetry between energy flux and momentum density becomes apparent. Question?
The second one, do you mean rho 1 will be 0?
Sorry, this one?
Yeah, on the right-hand side.
On the right-hand side. This is...
Rho I is 0.
No, this is definitely what I mean to write down here. So this is what I've done. I've taken advantage of the fact that I can write, let's see, do I have it down somewhere? Yeah. Yeah, so what I've done over here is I have written the fact, so U sub t, ut, is just the gamma factor, okay? And I didn't explicitly write out what t, the I components, but you get a similar factor there once that. So no, that is correct that way.
So that's why you mean the first and the second, they are the same.
Yeah, yeah. And I just want to emphasize, I mean, the key thing which I want to emphasize is when you do it in the physics that you guys have generally all seen up till now, it won't look that way. And that's two causes of that. One is you're not used to necessarily working in units where the speed of light is 1. And 2, rest energy is built into these definitions. That shifts things a little bit. The other thing which I want to emphasize is notice this is symmetric under exchange of indices. Okay? Now, it's obvious for dust. It comes right back to the fact that these guys, that those indices enter like so. It's an exterior product of the 4 velocity with itself. I'm not going to go through in detail, but there's a physical motivation that I will sketch in a few moments that argues that it must be symmetric like this in all physical cases. Okay? I have detailed, a detailed sketch of this. I keep using the word sketch because my mind wants to say proof, but it ain't a proof. Okay? It's sort of a motivation. And so I will post it for everyone to go through, but I will sort of illuminate it in a couple moments. Basically, if this is not true, if it's not the case that this is symmetric, a physical absurdity can be set up. And I'll describe that in a few moments. So most of the world is not dust. So this is a decent example for helping to understand things. But we are going to want to do more complicated and interesting examples. Pardon me just one second. Let me just check over this page. Yeah. So for us, the way that we are going to do this, there is a fairly general recipe that one can imagine applying to this. I'm going to save it for a little later in the class. It sort of borrows some techniques from field theory. Basically, if you can write down a Lagrangian density that describes the system that you're under study, there's a particular variation you can do that the stress energy tensor emerges from. But for now, the key thing which I want to sort of say is that we basically are going to deduce what the stress energy tensor looks like by essentially going into a particular frame. We'll call it the rest frame. It's usually the rest frame of some element of the material being studied, and thinking carefully about this physical definition of what the different components mean. Okay? This is not the most rigorous way to do it, but it's a good way to get started and to develop some intuition. Okay, so let me give one example that for many of us in astrophysics, this is probably the one stress energy tensor that we write down and use over and over and over again in our career, and it's rare we do anything more than this in many, many cases. This is called a perfect fluid. So what is perfect about a perfect fluid? That's, you know, it begs the question here. What is perfect referring to here? So a perfect fluid is a fluid in which there is no energy flow in what I will call the rest frame. I put rest in quotes because you have to sort of define it from the context of what your fluid is here. Basically what it means is I can find a frame in which each fluid element, there is no energy flow there. If a frame exists where that happens, this is a candidate to be a perfect fluid. And I also require there to be no lateral stresses. Lateral stresses refer to this Tij when I and j are not equal to one another. Okay, so this sort of refers to, imagine that I have some, let's say going into the board is the y direction. So if there's like some y stress that is somehow being transported in the x direction, that would be a lateral stress. Physically, this is actually, that kind of a stress is hugely important when one is studying fluids. Okay, and one characterizes it by a quantity known as the viscosity. Okay, viscosity tells me about how stress gets transported, or how momentum rather gets transported in a non-normal direction, against the direction in which the fluid is moving. So my perfect fluid has no viscosity. And I'll just conclude because I want to make there's a very important point here. A fluid that has no viscosity is a fluid that doesn't get anything wet. Okay? So this refers to when you pour water on yourself, the reason your hand gets wet is that there's some viscosity that actually prevents it, causes there to be sort of a shearing force, which causes the water to stick to your skin. So a perfect fluid, this has been described as the physics of dry water. Okay? So it is, anyone who's in applied math will know, they'll sort of roll their eyes and say, okay, fine, we'll do this sort of infant version of fluids first. And then a lot of the action and a lot of the fun comes from putting in viscosity and doing the real fluids. For the purposes of our class, what this boils down to is this tells me that the physics of this quantity is totally dominated by the fluid's energy density and its pressure. The pressure is an isotropic spatial stress. So in this particular frame where I have no energy being transported, then the stress energy tensor can be represented as energy density, as usual, up in the, oops, over there now, up in the TT component. There is no energy flux. By symmetry, if there's no energy flux, there is no momentum density. And my spatial stresses are totally isotropic, and none of them are lateral. So it just looks like this. The diagonal of rho P, P, P. Okay, as I said, this is actually something that we're going to use over and over and over again. This is actually and so you can actually consider my DUS, stress energy tensor, to be a perfect fluid with no pressure. Okay, so this actually subsumes this other one. I will, just for illustrative purposes, I'll show an example of a case that cannot be thought of as a perfect fluid, but we will tend to use this a lot in our class. And as I will demonstrate in just a moment, we're going to find that this ends up playing an important role in generating gravitational fields. And what's interesting about this is you guys are probably used to the idea that mass generates gravity, and then throw in a c squared that tells you energy is generating gravity. But it's also, we're going to see pressure generates gravity, okay? And it's connected to the mathematical structure of this guy here. So notice I've written an equal dot here, okay? So this is just the way this is represented in this particular frame. I would like to write this in a more covariant form, something that does not rely on me going into a particular frame of reference. So the trick which I'm going to use for this is if I think about that form there, so the row piece of it, clearly what I'm doing there is I'm picking out, that can be thought of as the energy density multiplied by the tensor product of the four velocity that describes a particular element of this fluid. So I can write, again, using this sort of abstract notation, this piece of it looks like this, okay? And so if I go into the frame, if I go into the rest frame of the fluid, that's just, my u is 1 and 0s in the spatial components. That builds my upper left-hand corner of this tensor. How do I get the rest of this? Well, to get the rest of it, these are all sort of picked out of components of the tensor that are orthogonal to u. And I put an Easter egg in p set 1. Okay, you guys developed a tensor that allows me to build, it's a geometric object that allows me to describe things that are orthogonal to a given 4 vector. So if I take the projection tensor that you guys built on p set 1, which looks like the metric plus the tensor product of a 4 vector with itself, that gives me the p's that go into that component, okay? Or if I write this in index notation, I can do it in 2 ways. I will also emphasize that there are a few moments in this class where I sort of urge you to take the sort of long-term memory synapses and switch them on. This is one of those moments. In a couple of lectures, we're going to introduce the principle of equivalence, which is the physical principle by which we're going to argue how we go from formulas that work in special relativity to formulas that work in general relativity. And by invoking the principle of equivalence, we're going to see that when we want to describe perfect fluids in a general space-time, not just in special relativity and general relativity, it's exactly this formula. I just need to modify what the metric means. Okay? But that will allow me to carry that over. Let me see. So my notes are a little bit disorganized here because this is a piece that every year I want to clean this bit up, and every year at this time of year I have 70 gajillion administrative tasks, and I end up getting behind schedule. So I will clean this up on the fly. So there's a couple points which I want to make about this. Let me do this point first. So by virtue of taking a graduate physics class, I'm confident you guys know about Newtonian gravity. One can write the field equation for Newtonian gravity as essentially a differential equation for the potential that governs the Newtonian gravitational interaction. So let's call phi sub g the Newtonian gravitational interaction. Whoops. And I can write a field equation that's governing it as essentially it's Poisson's equation. Okay? So the Laplace operator acting on that potential is up to a constant equal to the, we usually learn it in terms of mass density. We're working in units where the speed of light is equal to 1, so it could just as well be the energy density. So you've all kind of seen that. Now, if we think about how we're going to carry this forward and make gravity a relativistic interaction, this equation should right away make us suspicious, because we spent several minutes earlier today talking about the fact that this is not a scalar. Okay? This is a component of a tensor. Okay? A physical theory which tries to pick out just one component of a geometric tensor is not a healthy theory. Okay? It would be like if you had sort of learned in E&M that there was a preferred direction of the electric field. If there's a particular set of Maxwell's equations for Ex and a different set of Maxwell's equations for Ey, that would just be nonsense. Okay? Nature doesn't pick out spatial components of anyone as being particularly having some weight over the others. And the same thing holds in relativity for space-time. So when we make this into a relativistic theory, we're going to say, if this component of a tensor plays a large role in gravity, to make this into a geometric object that makes a large role in gravity, I'm going to have to, so let's call this my Newtonian equation. My Einsteinian equation, I'm going to put an equal sign in quotes here because there's a lot of details to fill in. But what's going to go on the right-hand side of this has to be something that involves the stress-energy tensor. Okay? Newton picks out one component of the stress-energy tensor. Relativity doesn't let me pick out particular components. So whatever I get when I do Einstein's gravity, the whole stress-energy tensor is going to be important in setting the source of my gravity. That then sort of says, well, then what the heck do you do with this left-hand side? That is, in fact, going to be, starting probably on Tuesday, the subject of the next couple of lectures, basically going all the way up to spring break. Okay, the week before spring break is when we complete the story of what goes on the right-hand side, the left-hand side of this equation. But what I will tell you is that it is indeed going to involve two derivatives of a potential-like object. And the potential-like object is actually going to turn out to be the metric of space-time. Okay? So that's kind of where we're going with this. All right, so let's do a little bit more physics with the stress-energy tensor. So I have somewhat more detailed notes, which I will post online, which I am not going to go through in great detail here, but I'm going to kind of sketch this. So one is that I would like to prove, again, that word is a little bit of an overstatement, but at least motivate the symmetry of this tensor. Okay, I'm just going to focus on the spatial bits of this. That'll be enough. Okay, like I said, you can kind of see that T0I and Ti0 are the same thing by thinking about the physical meaning of form momentum and what a flux of form momentum is. This one, there's kind of a cute calculation you can do. So imagine you have some little cube of stuff. Could be immersed in some field or fluid, something that is described by a field of stress energy. And so, to start out with, let's look at how the flux of, remember what T alpha beta, or really Tij tells me about, is the flux of momentum in a particular direction. It's telling me about the amount of momentum going into this box on one side and coming out on the other. Okay? So I'm going to look at the momentum flux into and out of this box. And so what I'm going to do is let's look at the momentum going into the sides that are, so let's call this the top and the bottom here. What I'm going to do then is number the four sides, the other four sides of the box, not the top and the bottom. So let's call this side, which is sort of facing away from us here, that's side 1. The one that is facing us, that sort of points out in the x direction, I'll call that 2. This side here, I will call 3. And the one that is on the back, I will call 4. Apologies for the little bit of a busy picture here. But just what you want to do is sort of imagine you have this cube in front of you, and you go around and label the four sides. What we'd like to do is calculate what is the force that is flowing through each of these four sides. Okay, 1, 2, 3, and 4. Let's ignore the top and the bottom for just a second. I'll describe why that is in just a moment. So if I look at the force on face 1, okay? Well, face 1, it is, pardon me, I mislabeled my sides. I want to be synced up with my notes, and so I realize it's annoying, and I'm very sorry about that, but if I mess this up, I will get out of sync with what I have written down. So the one that is facing us is side 1, 2 is on the right-hand side, 3 is the back, 4 is on the left-hand side. My apologies for that, but I think it's important we get that right so I don't get out of sync with myself. So the total force on face 1 is what I get by basically adding up all the flux of momentum flowing through face 1. So force on face 1, that is the ith component of that, is what I get when I integrate that over face 1, which is normal to the x-axis. Each side of the cube is little l, so it's Tix L squared. Okay? Force on face 2. Okay, now this is the one that is normal to the y-axis. And so this guy looks like Tiy L squared. Okay, and as you continue this, F3, you look at that, and you know, if you assume that this thing is small, it's approximately the same as the force on F1. It'll become equal in the limit of the cube becoming infinitesimally small. And this is approximately the same as the force on face 2. So that tells us that there's no unbalanced force on this thing, which is great. Basically, it means that there's no unbalanced force causing this little element to accelerate away. One of the reasons why I am focusing on these four sides, though, is I would also like to consider torques that are acting on this thing. And here's where I'm going to skip over a couple of details and just leave a few notes for you guys to look at, because we're a little short on time with other things. This calculation is straightforward, but it gets, I already screwed up a detail here. I don't want to sort of risk messing up a few other things. What I want to do is consider the torques about an axis that sort of runs through the middle of this thing, but goes from the top and the bottom of this. Okay, so go through and just add up all the torques associated with these little forces about an axis in the center of that goes through the center of this cube. Okay, so I'm going to, like I said, I'm going to leave out the details, but basically you go through and you do the usual R cross F to get the forces, the torques associated with each of these different faces. And what you'll find when you do this is that there is a net torque that looks like L cubed times Txy minus Tyx. Again, though, this scales with the size of the cube, right? So you look at this and kind of go, well, who cares? You know, it's a little bit there. Maybe it spins up a little bit. But in the limit of this thing going to 0, there's no net effect. Well, let's be a little bit careful about this. What is the moment of inertia of this cube? I don't know exactly, but I know that it's going to be something like the mass of this cube. We'll call that L cubed times its mass density, or its energy density. And it's going to involve 2 powers of the only length scale characterizing this thing. And there'll be some prefactor alpha. There'll be some number that's related to the geometry of this, okay? An integral or two will easily work out what the alpha is and make this more precise. But the key bit, which I want to emphasize, is that this is something that scales as the size to the 5th power. So yeah, the torque vanishes as L goes to 0, but it does so with the cubed power. It doesn't vanish as quickly as the moment of inertia vanishes. And I'll remind you, the angular acceleration of the cube theta double dot is the torque divided by the moment of inertia. So this is something that is proportional to Txy minus Tyx divided by L squared. So yeah, the torque does vanish as L goes to 0, but the moment of inertia vanishes more rapidly as L goes to 0. And that sort of suggests that if we're in a screwy universe, little microscopic vortices are just going to start randomly oscillating in any cup of water that you pour in front of you. Now, I don't have a proof that nature abhors that, but it seems pretty screwy. And so the case that most textbooks make at this point is to say physics indicates we must have Txy strikingly equal to Tyx in all cases, independent of what the size of this thing is. Okay, that had better just be a bloody 0 in the numerator in order to prevent this physical absurdity from being set up. Repeat the exercise by looking at torques around the other axes, and that drives you to the statement that this thing must, in general, be spatially symmetric. And again, physics of the way that energy and momentum behave in relativity makes our sort of time-space component symmetric as well. I emphasize this is not a proof. This is really just a physical motivation. This is the kind of thing that I'm a bloody astrophysicist. I like this kind of stuff. There is a different way of developing the stress energy tensor, as I said, that comes from a variational principle, sort of based on sort of quantum field theoretic type of methods. And the symmetry in that case is manifest. Okay, it really does sort of come up. But this is a good way of just motivating the fact that you're not going to have any non-symmetric stress energy tensors. Okay? If you did, you would have really bizarre matter. All right. Now, the stress energy tensor has this physical interpretation that it tells me about the flow of energy and the flow of momentum in space-time. As such, it is the tool by which we are going to put conservation of energy and conservation of momentum into our theory. And the way we're going to do this is with a remarkably simple equation. The space-time divergence of T alpha beta must equal 0. This is a covariant formulation of both conservation of energy and conservation of momentum. And if you want to say, well, which one? Is it energy or is it momentum? You can't say that in general. Okay? I can only say that after I have picked a particular reference frame, because it's only once I have defined time and I've defined space that I've actually defined energy and momentum. Okay? Prior to choosing a particular reference frame, all I have is form momentum. One observer's energy is another observer's superposition of energy and momentum. Once I have picked a particular frame, then if I evaluate d alpha of t alpha, either 0 or t, this is what conservation of energy looks like in that frame. So in that frame, here is conservation of energy. And I can fit it. Second. No. I had it right the first time. Yeah. Sorry, just trying to make sure I got my indices lined up properly. So, apologies, you can't quite read the bottom one so well. Top one is conservation of energy in that particular frame. Second one is conservation of momentum in that particular frame. Okay? And again, the key thing which I wanted to emphasize is the covariant statement basically puts both of them together into a single equation. I can only sensibly state conservation of energy and conservation of momentum according to some particular observer. Now, I can repeat the game that I had done before with the number vector and turn these conservation laws into integral equations as well. Let me do it for energy. So if I take that integral equation, integrate over a 3-volume, or if you prefer, I can take the original covariant formulation, integrate that over a 4-volume, with a little bit of manipulation akin to the way I manipulated the integrals associated with the number vector in the previous lecture. You can write down a law that looks like this. Okay, and so this, again, what I've done here is I've chosen a particular set of time-like coordinates. And the language that we often use in relativity is we basically say I'm going to take a single slice of time. And I would say that the rate of change of energy, so integrate energy over a volume, is the total energy in that V3. The rate of change of that thing is balanced by the amount of energy flowing into or out of through the boundaries of that volume. Okay? Add an extra index here, so make make one of these be a J, make this guy be a J, and you've got a similar statement for the conservation of momentum. Okay? This is a particular trick. I have a set of typed up notes that just sort of clean this up a little bit, and they're basically exactly this point, but I'll put them online after today's lecture. You're going to want to use this on one of the p-set problems this week. Okay, so you guys are going to do a couple exercises that involves integrating and actually finding essentially moments of the left-hand side of this thing. Okay, you're going to do a few exercises where you take advantage of this formulation of conservation of energy and momentum to derive a few identities involving the stress-energy tensor, one of which is another Easter egg that we're going to use quite a bit in a future lecture. All right, so let me just wrap up our discussion of the stress-energy tensor by just doing 2 more examples, and then I'm going to sort of begin switching gears a little bit. So far, I have only described, essentially, I've really only described perfect fluids. Okay? Dust is a perfect fluid with no pressure. There are a lot of other kinds of materials that we want to work with in the universe. One of them, which it's unlikely many of you are going to use this, but it's actually the stress-energy tensor on which I have built, well, I guess Alex is going to use it a little bit. I have built a big chunk of my career. Is suppose you have, we kind of talked a little bit about how the force velocity and the force momentum are really only good for talking about like the kinematics of particles. Well, actually, particles aren't a bad thing to focus on in some of your studies. Okay, and much of my research is actually based on the idea of thinking about a binary system as being one member being a black hole and its companion being a particle-like object it's a particular limit of it, a particle-like object that orbits it. So a really simple stress-energy tensor, and I'm just throwing it out here because I think it nicely illustrates the principle. A point particle with rest mass, we'll call it m0. And I'm going to say it's moving on a particular world line through space-time. So the way we define a world line is we just say it's some 4 vector that describes the displacement of this thing from some chosen origin. And it's generally most convenient to parameterize it by the proper time of whatever object or creature is moving on that world line. And so it's a lot like dust, only there's no volume, right? It's sort of like one particle of dust. And so the stress-energy tensor we use for this let me back up for just a second here. When you guys learned about electricity and magnetism, okay, one of the first things you learn about are point charges. And then a little bit later, you learn about charge distributions, and you have charge densities. Okay? And then usually at some point in a class that's often like junior level E&M, we say, how do you describe the density of a point charge? And that's where you learn about the Dirac delta function. Well, if I have a point particle, I'm going to need to describe this thing's energy density as essentially a Dirac delta function. And so what we do is imagining that these things, so this is the forward velocity of that body, they might be functions of time as this guy is moving along here. What we do is we introduce a Dirac delta function as this thing moves along through space-time. And what this does, you can check the dimensions. This gives me exactly what we need in order to have something that's dimensionally correct and has all the symmetries and all the properties that describe a particle moving with a particular forward velocity through space-time. Now, you might want to just, it's the thing which I kind of want to pause on for a second. You go, what the hell do you do with this, right? That's kind of inconvenient. Well, the trick we use to sort of clean up that Dirac delta function is it's very much like what you do when you encounter multidimensional delta functions in basic physics. You just build it out of a bunch of one-dimensional delta functions. Okay. Likewise, you'll have a term with the y component and the z component. And then you use the rule that if I integrate a function of x against a delta function whose argument is itself a function of x, I evaluate that function at the zeros of g, so let's say x0 is where g has a 0, normalizing to the first derivative of g evaluated at that 0. So when you put all of that together, it basically means you can do this somewhat abstract integral formally. I mean, exactly. You can just do it analytically. And what you do is you choose one of the delta functions to apply it to. Traditionally, people apply it to the time-like component. And what is the derivative of the world line z component with respect to proper time? It's the 0 component of the forward velocity. So you just divide by the 0 component of the forward velocity, and then you're left with a three-dimensional delta function for the spatial trajectory of this thing through all of space. So this is an example of one that just, again, kind of the intuition is one of the things I want to emphasize. Notice this has the symmetries that we want it to have. It's not hard to show that this, you can think of this as essentially being kind of like a gamma factor. This all ends up giving me just what we need for this thing to have the right transformation properties. And it does, in fact, play a role in some, well, I'll just say in some research that's near and dear to my heart. Let me do another example. Suppose you want to know the stress energy tensor associated with a given electric and magnetic field. Well, first, let me just quote for you the exact answer, which is most compactly written if we use that Faraday tensor F, which describes electromagnetic fields in a frame-independent fashion, the way that I introduced it in the last lecture. So in units where basically everything but pi is set equal to 1, it ends up turning into this. Okay, so that's a bit of a mouthful. Let's go in and look at particular components of it, though. Okay, so let's say I go into a particular frame. I fill in my Faraday tensor with the form of the electromagnetic field that I introduced last time, and I'll just go through and I'll evaluate all the different components of this thing. So what you find when you fill this in is your T00 component one over 8 pi e squared plus b squared. Okay, that's good. Okay, hopefully you all remember from basic E&M, the energy density of an E field is E squared over 8 pi in the right system of units. Energy density of a B field is B squared over 8 pi if you work in God's units. Let's do the time-space component. So again, hack through that mess there. This is going to be something that is a vector. In fact, it's the pointing vector. Okay? Could it be anything else? If you use the recipe that I sort of suggested as the easiest way to approach this, this is kind of what you would have guessed for something like that. The bit that's actually kind of hard is then trying to get the spatial stresses of this thing. And here, I don't have any great intuition for this one to convey to you. It's derived in textbooks like Griffiths and Jackson, so I'll just quote for you the result. So you get one term that looks like e squared plus b squared on the diagonals. But then there's a correction. Which looks like this. I want to just quickly call out one example so you can see what the significance of this example is. So suppose you have something like a pair of capacitors, right? And there's just a uniform electric field between them. You want to evaluate the stress energy tensor between those pairs of capacitors. So my spatial electric field, let's say it just points in the x direction, and it's constant. So when you actually evaluate this guy, there's no energy flow. There's no magnetic field, so there's no pointing vector. You, of course, have e squared over 8 pi for your energy density. Okay, very different from a perfect fluid. Okay, and this kind of makes sense. That's sort of telling you that there is a stress that, if you have a pair of plane parallel capacitors, you tend to attract the plates to each other, right? But there's a pressure associated with that electric field that actually goes in the other directions. Okay, this is your x direction, this is y and z. And as a consequence of this, so there's some stuff which we're not going to do too much with in this class, but I may give you some pointers on this. Electric and magnetic fields generate pressures, at least in certain directions. They kind of generate like an anisotropic pressure. And when we start coupling this to gravity, you can get electric fields and magnetic fields that contribute non-negligibly to the gravity of their object. That is it for the stress energy tensor. As I said, we are going to use this guy over and over and over again. And the reason for this does come back to that little motivation that I gave probably about 45 minutes ago, where we sort of looked at the Newtonian field equation and then said, picking out a particular scalar as the source of gravity makes no sense in a relativistic covariant theory. It's got to be the whole tensor. And indeed, this is the one, well, not necessarily the E&M one, but the general notion of a stress energy tensor is the one that we are going to use for that. So we have about 10 minutes left. And so I would like to start the process of switching gears. Before I do that, are there any questions? All right, I will clean the board. So the reason we are switching gears is we now have probably the most important physical tools that we need in order to start thinking about making a relativistic theory of gravity. But we need a few more mathematical tools. In particular, I'm going to argue in a couple of lectures that flat spacetime is not sufficient for us to build a theory of gravity. We're going to need to, first of all, you're going to have to understand what that means, and we're not quite ready to go there. So for now, it's just fancy words. But I'm going to have to introduce some kind of a notion of curvature into things. Okay, what does that even mean, really? We need to have the tools to do that. And so as a prelude to going in that direction, I will call this my prelude to curvature. What we're going to start doing is flat spacetime in curvilinear coordinates. And the importance of doing this, why this is going to be useful to us, is that it will introduce so it'll keep the physics simple. It's still going to be special relativity. But it's now going to be special relativity using a mathematical structure in which the basis vectors are no longer constant. Okay? And so that's going to allow us to begin making a couple of the mathematical tools that are necessary to build gravity into this theory. So we'll start by replacing this with just simple plane polar coordinates. Okay? Mapped in the usual way. So if you want to go back and forth, well, at least one-way transformation. I build x and y from r and phi in that usual way. There's an inverse mapping as well, which involves trig functions, so I'm not going to write it down. One point which I really want to emphasize here is we are going to continue to use a coordinate basis. And let me remind you what that means. So a coordinate basis means that the differential displacement vector from an event A to a nearby event B is simply related by differentials of my coordinate contracted onto my basis vectors. But when I'm working in a curvilinear coordinate system like this, that means one of them has a somewhat different form from what you are used to. Okay? When you guys talk about the differential of a displacement in just about every physics class up till now, if you have a differential angle, you'd want to throw an r into here so that this has the dimensions of length. We ain't going to do that. Okay? And so what this means, since this is an angle, every component of this has the dimensions of length. That means that my basis vector is going to be something that has the dimensions of length associated with it. Okay? This, in turn, means that this is not going to be a normal basis. Okay? That's unfortunately a somewhat loaded word. What I mean by that is that it has not been normalized. But given that you guys have spent all of your career thinking about the dot product of a unit vector with itself, of a basis vector with itself being equal to 1, the other meaning of normal might be good for you too. The key thing which I want to emphasize here is E phi dot E phi does not equal 1. One other little bit of notation which I would like to introduce. So we are going to want to talk about transformations between different representations. Okay, we've done this so far. We have generally focused on moving between different reference frames. I want to generalize this notion, and I'm going to tweak my notation a little bit to indicate the difference. Okay, so I'm going to call capital L alpha mu bar be what I get when I just look at the variation of the alpha coordinate system, the unbarred coordinate system with the barred one. Okay? So this is just, there's no deep things here. I just want you to be familiar with the notation which I'm going to use. I will always reserve lambda for the Lorentz transformation. Okay? So in the interest of time, I'll write down one of these. So this sort of means, like, for instance, suppose that I'm transforming. Let's let barred indicate my polar coordinates, unbarred be Cartesian. These things are surprisingly sticky sometimes. Okay? So if I want to transform in one direction between my barred and my unbarred ones, this matrix will go through it, and it looks like this. So this is the thing which I will call L alpha mu bar. Okay, in my notes, I also give the inverse transformation, and I will actually write, you know what, I have a minute. I will write that one down as well. If you want to know how to go in the other direction, it's just the matrix that inverts this. And the reason I decided to take the extra 30 seconds or so to write this down is I want to call out the fact that in this kind of a transformation, because of the fact that this is a coordinate basis that has this somewhat unusual property, different elements of the matrix have different dimensions. Okay? It's a feature, not a bug. Okay? So this is going to show up. I'm going to do a couple more calculations with this a little bit tomorrow. Sorry, not tomorrow, on Tuesday. This is going to show up in the way the metric looks. Okay, the metric is going to have a very different character in this coordinate system. And we're going to see the way in which it basically boils down to is it's going to pick up a non-trivial functional form. It's not going to just be a constant. And that fundamentally reflects the fact that the basis vectors are not constant anymore. Okay? We'll end it there. So let me just pick it up where we stopped last time. So we are beginning to discuss how we are going to sort of do a geometrical approach to physics using a more general set of coordinates now. So we began talking about how things change when I discuss special relativity. So for the moment, keeping ourselves just at special relativity. We, by the way, are going to begin lifting our assumptions that it is simply special relativity fairly soon. But to set that up, I need to start thinking about how to work in more general coordinate systems. Okay, so we're going to do it in the simplest possible curvilinear coordinates. So it's basically just going from Cartesian coordinates in the spatial sector to plane polar coordinates. One of the things which I have emphasized a few times, and I'm going to continue to hammer on, is that these are a little bit different from the curvilinear coordinates that you are used to in your past life. Okay, in particular, if I write out the displacement, the little vector of a displacement element in the usual way, I am using what's called a coordinate basis, which means that the vector dx is related to the displacement, the differential of the coordinates by just that thing contracted with all the basis vectors. And so what that means is I have a little displacement in time, which looks normal, displacement in radius, which looks normal, displacement in the z direction, which looks normal, and a displacement in angle, which does not. Okay? In order for this whole thing to be dimensionally consistent, that's telling me E phi has to have the dimensions of length, and that is a feature, not a bug. Okay. Last time we introduced the matrix that allows me to convert between one coordinate system and another. So just basically the matrix, it's sort of a Jacobian matrix, it's the matrix of partials between the two coordinate systems. And this idea that things, they look a little weird, right? So the way I did that was I didn't actually write it out, but I did the usual mapping between x, y, and r and phi, worked out all of my derivatives. And sure enough, you got something that looks very standard with the possible exception of these r's that are appearing in here. So notice the elements of this matrix. These do not have consistent units. Again, feature, not bug. This guy is basically just the inverse of that. This is the matrix that affects the coordinate system in the opposite direction. And notice in this case, you have some elements where their units are 1 over length. OK, so let's just continue to sort of catalog what some of the things we're going to be working with look like in this new coordinate representation. And this will lead us to introduce one of the mathematical objects that we are going to use extensively as we move forward in studying this subject. So what I want to do next is look at what my basis vectors look like. So what I want to do is characterize what my ER and my E phi look like. And these are going to look very familiar from your intuition from having studied things like E and M in non-Cartesian coordinates. So your ER is just related to the original Cartesian basis vectors like so. Okay, and if you like, you can easily read that out by performing the following matrix multiplication on the original Cartesian basis vectors. Your E phi perhaps looks a little wacky. Okay, so you can see the length coming into play there. A good way to think about this is if you sort of, your intuition about unit vectors, your intuition about basis vectors, I have to be careful with this language myself. Your intuition about basis vectors is typically that they are unit vectors. Okay? These are not unit vectors. They do form a nice basis, but they are not unit vectors. In particular, the basic idea we're going to go with here is that E phi, it's always going to sort of point in the tangential direction, but no matter where I put it in radius, I want that vector to always sort of subtend the same amount of angle. In order to do that, its length needs to grow with r. Okay? So that's where that's a little bit different from your intuition. And there's a very good reason for this, which we will get to hopefully well before the end of today's class. So last time when we first began to talk about tensors, a couple of lectures ago, the first tensor I gave you, so confining ourselves just to Cartesian coordinates, was the metric, which was originally introduced as this mathematical object that came at looking at dot products between basis vectors. It's essentially a tensor that allows me to feed in two displacements and get the invariant interval between those displacements that comes out of that. I am going to continue to call the dot product of two basis vectors the metric. But I'm going to use a slightly different symbol for this. I'm going to call this G alpha beta. Okay? In the coordinate representation that we are using right now, so in plane polar coordinates, this becomes, whoops, you can work it out from what I've written down right here. This is just the diagonal of minus 1, 1, r squared, 1. Okay, so this equals dot here. This is, I'll put PPC for plane polar coordinates under that. And then using that, you know that you can always work out the invariant displacement between two events. It's always going to be the metric contracted with the differential displacement interval, or excuse me, the differential displacement element. And this is going to be minus dt squared plus dr squared plus r squared d phi squared plus dz squared. That, I hope, makes a lot of sense. Okay, this is exactly what you would expect. If I have two events that are separated in plane polar coordinates by dt, dr, d phi, dz, this is what the distance between them should be. Okay? So the fact that my basis vectors have this slightly annoying form associated with them, you know, it all sort of comes out in the wash here. Remember, at the end of the day, if we think about quantities that are representation independent, and that's going to be the key thing when you assemble scalars out of these things, you know, the individual tensor components, they can be a little bit confusing sometimes. Okay? But they are not things that we measure. They are not things that really characterize what we are going to be working with when we really want to get into the physics, unless we're very careful about it. This is something you can measure. Okay? And so, sure enough, it comes out and it's got a good meaning to it. Let me just wrap up one last thing before I talk about sort of where we're going with this. So just for completeness, let me write down the basis 1 forms. Just as the basis vectors had a bit of a funny form associated with them, you're going to find the basis 1 forms likewise have a bit of a funny form associated with them. And the way I'm going to get these, and so these are going to be the Cartesian basis 1 forms. Basically, I'm not carefully proving all these relationships at this point. Okay, y'all know how to do that. I'm just using line up the indices rule. And then when you do that, you get this. And likewise, your basis 1 form for the axial direction. I'll just write down the result. It's going to look like this. Okay. So the key place where all of this, so right now these are all just sort of definitions. Nothing I've done here should be anything that even approaches a surprise, I hope. You know, just given that you guys have done, the key thing that's probably new is just all this garbage associated with coordinate bases, these vector factors of r and 1 over r that are popping up. But provided you're willing to sort of swallow your discomfort and go through the motions, these are not difficult calculations. The key place where all of this really matters is going to be when we calculate derivatives of things. Okay, it'll turn out there's an important role when we talk about integrals as well a little bit later, but let's just say that. So for now, we'll focus on derivatives. So all the derivatives that we've been looking at so far, we have indeed done a couple calculations where we've computed the derivatives of various vector-valued and tensor-valued quantities. And it was helped by the fact that all the bases, when I worked in Cartesian coordinates, are constant. Well, that's not the case now. So now we need to account for the fact that the bases all vary with our coordinates. So let me just quickly make a catalog of all the non-trivial. There's basically 4 in this one where I'm